It's like 5-second delays, so.
You want me to leave?
Oh, hello, Dolores. Good to see you.
Hi. Good to see you too.
Looking forward to your talk.
Thank you.
We've got a bunch of donuts here, so we are very ready. Samir, next time you should come to the.
Pavel, how are you?
lab.
That would actually be an excellent idea, except I have
Yeah.
childcare today morning.
Oh,
I'm gonna run out in the middle to take care of the kids.
Okay.
But yes, I have to come
2020
find you on the campus though.
Yeah. 2024 goals. That'll be perfect.
I'll be having
Okay.
I'll have
Sorry.
my art class attend this for a short while.
All right. I think I put the YouTube streaming link on the website, or maybe it'll be there in a minute or so once GitHub finishes compiling our HTML or whatever it's doing.
I haven't seen anything I didn't see outside.
I'm sure it'll holler at when we get to.
All right. Yes, the stream is working. Great. All right, and I'll be kicking it off in just a minute or so.
Y'all are a quiet group this morning.
Yeah, well, let's kick it off. Let's not keep the people waiting. So
Oh, you want to do intro? Oh yeah, because of schedule. Should we?
yeah, we just have too many speakers this year. We have to kick it off before the main talks start.
Oh,
We
okay.
had to make some allowances to get everyone's talk in. So yeah, welcome everyone. It's good to see you all. It's been a whole year since the last FP Talks, and it's great to have the community together. So welcome, first of all, of course, welcome all of our speakers. And then, of course, welcome everyone who is participating as well. I hope you enjoy these talks. I personally am super excited for them. This is your first time to FP Bench, then I'm going to give like a brief intro here of what we're all about. If it's not your first time, then you'll have a pretty good idea of what FP Bench is about. So we're all about numerics. We're about numerics spanning from hardware to software, spanning from theory to applications. We're interested in numerics anywhere it's used, whether it's robotics or graphics or machine learning. And we'll get a hint of that diversity at the talks today. At least I hope so. We're basically all here because you probably know this, numerics is important. It's getting increasingly important over time as people find new and exciting ways to apply it, whether again, that's robotics or graphics or machine learning or climate science or simulation or all these other domains where people are applying numerics, running into new problems and new ways of fixing them. And then of course, that means there's a huge opportunity also by working on numerics to make an impact in the world. Actually, one of my favorite things working in numerics is getting to talk to folks applying it in all sorts of interesting domains, right? Domains where I didn't even know. I get to learn something about science or about the climate or about whatever it is that they're working on. So given like how important numerics is, the idea of FPTalks and FPBench is kind of combine these pieces, combine theory and application, combine hardware and software. And the idea is our FPBench formula is that if you put these together, maybe there's some rounding error, but you're pretty close to getting some new advances in numerics, sparking ideas, getting people talking to each other, initializing new collaborations. So that's what we're here to do. That's the big plan. Let me tell you a little bit about the FPBench project that kind of hosts this event. It's a project that's probably getting close to a decade old at this point. And the idea is to do some community building in the numerics community and also put together some community resources that numerics researchers can make use of. So the community building, that's become kind of the big focus of the project. And that's stuff like the Slack, which hopefully all of you are on. It's where what we'll be using to do question and answers for this FPTalks. But it's also a place that you can ask questions or post papers or ask for help with someone else's tool even outside of this conference. We also hold these monthly FPBench community meetings. These are the first Thursday of every month at 9 a.m. Pacific time. And these are kind of lightweight, informal venues where you can give demos, you can discuss some ongoing work. We've had some excellent discussions on topics like teaching. We've also had fantastic demos of all sorts of new tools or problems that people have run into. I remember Schwabe from Adobe had an excellent talk on some experiments they'd done to try to validate a selection of libraries. So those can be a lot of fun. And we still have slots open for that, I think, in December. So if you're interested in talking to one of those, do get in touch with me or with Zach. And then also, of course, we have this FPBench workshop. I don't need to say too much about it because you are at it, but this is the 4th time we're hosting it. And I think we've refined the formula over time, and I'm pretty excited about it. So this is one thing that FPBench is doing, hold these community building events. And then the other thing that FPBench is about is collecting some community resources. So for example, we've got a collection of benchmarks. These are standardized. We have them cross-linked to papers where they're used in. There's quite a diversity of different floating point operations used in different cases, come from different domains. And these have been used in quite a number of papers right now. And it says 30 plus papers, and that's probably growing every year that I put this up. There's also a directory of floating point tools. So this is maintained by Mike Lamb, who I saw here just a moment ago. And that's got a list of different floating point tools with links to resources like papers, GitHub repos, and also tracks a bit of the status of the tool. So if you're kind of new to floating point, you're looking for a tool that can do a particular thing, or even if you're looking for like related work to compare some project you're working on, that's a great place to look. And then finally, we have some standards. We've written up some standardized benchmark formats, some standardized benchmark measurements for mixed precision computations, for tensor computations. So that's helpful if you're developing a tool. That can be a good input format for you to make use of. So that's the idea of FPBench. And of course, hopefully this workshop is maybe an intro to the project for all of you who are new to it. And you can find out more of that on fpbench.org. So that's where the talk schedule is posted, and then the rest of the site has all these other resources and links to these community building activities. So let me tell you a little bit about the schedule. We have 3 sessions, one starting at 8, one starting at 9:30, and one starting at 11. And then in between those, there'll be half-hour breaks. Those half-hour breaks, I'll still be here. The Zoom will be on. Discussion will continue on Slack. And if previous FPTalks workshops or any hint, you'll see some discussion ongoing for some of the first session talks during those breaks. But of course, it's also a good time to, brew a new pot of coffee or whatever you need to do. So just some quick logistics around that. Please keep your microphone muted. Of course, you've done these before. If you have questions, I'll be posting a thread in the FPTalks 23 channel for every talk that you have. And if you have questions for the speaker, just put them in there. It's much easier to do that as the talk is ongoing, the moment a question pops into your head. When the speaker's done, there will be a Q&A session for people who want to ask their questions out loud. But the thread of questions on Slack, that'll continue. And we've often had that turn into ongoing discussions in previous FPTalks. And then, of course, I think Zach pointed this out, but maybe you've just joined. These talks are all being recorded. They're also being live streamed to YouTube. So all of the talks will end up on YouTube. If you miss a talk, you have to teach a class, you have to step out for some reason, you can find those on YouTube right after the talk. If anything goes wrong, you can contact me. I'm at Pavel Panchah on the Slack, or you can ask in this channel #support, which you may have automatically been joined to. But I don't want to take up too much more of the time. Point of this was just to say welcome and then to transition us to our first session. So let me quit out of this and switch on over to Edward. As soon as you're ready, we've got a minute or two of lead time.
Yeah, do you want to start early or wait until we hit?
let's wait a few minutes. Let's try to
Okay.
stay on time. I don't know. Some people might be joining like the moment they can. But I hope everyone's pumped. Yeah, while we're waiting, I can point out some fun statistics. So this year is a little bigger than last year, so we're continuing to grow bit by bit. We've got, I think, 60 registrations from 30 different institutional affiliations. So it's giving you quite a sense of just how diverse the group of attendees is. So they're not all here right now, but people join and leave over time.
Pavel, can you remind us how we want to do Q&A?
Yeah, again, the way to do Q&A, if you're on the Slack, you should already be in this channel called FPTalks 23. And the moment Edward starts talking, I'll put a message in the Slack saying, questions for Edward's talk on GPU, rule everything around me, please put them right here. And then you can just comment in that thread. We'll take some of those questions for Q&A after the talk. Typically, we run out of time. There's more questions than we can get to. And then, hopefully Edward has a moment to look at some of the questions after his talk and answer them. Or during the break or something like that. I just made that thread.
Okay, let's go ahead and get started. It's 11 o'clock. Hi, everyone. I'm
Yes.
Edward. I'm an engineer at Meta. I work predominantly on PyTorch, the deep learning framework. I don't normally come to FPTalks, but I do care about floating point computation because that's what deep learning is doing all the time. And Pavel graciously asked me to come and talk about, hey, what's going on? What in the world of machine learning is going on with floating point computation. And I thought about this, and in the end, I was like, well, what's going on is that GPUs rule everything around me. And so in this talk, I just want to tell you about, why GPUs are such a big influence on the deep learning landscape. And really, and this is important to emphasize because I do know a little bit about scientific computing from my previous life, and deep learning is like just a really, really strange alternate universe to like the normal like floating point questions we ask in scientific computing. And like one really good example of this is sort of what is going on with just floating point representations in deep learning, right? Like double precision, no one uses double precision in deep learning. Yes, if you're doing a simulation, that would be totally what you would want. But in deep learning, we're training these neural networks, and like there's a bunch of things that we're trying to do, and it turns out that we don't actually need that level of precision most of the time to get the results we want to do. In fact, people are like, hey, 256 floating point values is more than enough for the things that I want to do. And that's sort of where things are marching to. And I just want to explain why this is a thing. And there's going to be three parts to this explanation, right? Which is like, why are GPUs such a strange universe? Well, first, they're massively parallel, right? Like, so the main idea behind a GPU and why it used to be a graphics processing unit was you wanted to do a bunch of compute to like figure out what every pixel on your monitor wanted to be. And it turns out that like this kind of hardware is also really good for doing matrix multiplies and evaluating neural networks. So you've got these massively parallel GPUs, but actually the circuitry on them is very heterogeneous. Like you actually need silicon to like do various operations, and some operations we put silicon into the GPUs to be able to do them very quickly, and some operations we didn't. And so that's also like a big question mark when we're designing algorithms, when we're trying to figure out how to make things go faster on the GPUs. What we actually have on the silicon matters a lot for us. And that's probably not too surprising, but what is kind of different is like if you think about like conventional CPU computation, the basic architecture, what you expect to get on them doesn't change all that much, but it actually changes a lot from generation to generation on GPUs. And so, in my previous slide, I was like, oh yeah, we're going to, 8-bit floating point numbers, right? This would be like completely out of the question for conventional CPUs. Like, who's going to send you hardware that actually has FP8 circuitry? But like, that is what is happening with NVIDIA's latest Hopper series of compute. And the last part of this is memory bandwidth, because a huge part of like, computation is actually just getting the data off in the first place. And, when you think about these like really big, interesting models, like, GPT-4 that people are talking about, it's lots and lots of floating point parameters. And so actually getting them to the streaming multiprocessors to actually do compute on them, that's a big problem. And it also influences what exactly you're going to do. And so we can like see this in a microcosm. If we just like look at one of the like tech sheets for example, the upcoming Hopper architecture. This is for the H100 GPU, and this is something you'd put in a data center, and then you like train giant models with it. And you can see just looking at this data sheet, what exactly are they talking about? Well, they've got all of these different, things, FP64 tensor core. That's another thing I'll mention about it as well. And all of these, they talk about how many, flops you get for any given piece of computation you want to do. And one thing I want to point out is that the standard comparison with H100 would be the A100, which is the like current like sort of big GPU card that you can use for server compute. And when you like look at the difference, flip between the two tech sheets, they actually 3x'd the number of flops for like floating point computation, but they only 2x'd the memory bandwidth in this situation. So, there's like this tension going on here where like the hardware constraints matter a lot for how you go about designing software. Another answer for why floating point computation is so strange is that, hey, if you're doing a simulation, you really want to approximate real numbers as well as you can. But in deep learning, right, we're all about fiddling around with the weights to like do better at some task. And so your network can often work around lack of precision. And so this is sort of the name of the game in a lot of situations when you're training neural networks. Okay, so I have I have 5 minutes, so let's go. So okay, massive parallelism. So what do I mean by massive parallelism? Well, I'm talking about like teraflops worth of compute, and there's a lot of silicon, there's a lot of processors. How exactly does the GPU get all of this compute? Well, they just have a lot of silicon for it. So this is a picture of a streaming multiprocessor, which is the like general, it's like a unit of compute on the GPU, and each of these FP32 units is something that can do an FP32 instruction per cycle, actually 2 in the case of H100s. And you see we jammed all of these onto this streaming multiprocessor. And so unlike a CPU, these all have to do exactly the same compute from step to step. You can't like do different things like a normal CPU. You have to do exactly the same thing. So it's really good when you're very parallel. And then what they do is they paste a huge number of these SMs into a single chip. And, there's a cache that they access and then the actual RAM in question. So you get about like 80 gigabytes of memory on the like really beefy server cards. And, you have to plan your algorithms around this because, the GPUs are really, really good at running, massively parallel compute very fast. But then if you want to like communicate, well, that's kind of expensive. And like one of the pain points for optimizing algorithms on GPUs is like managing the caches on the hierarchy to make things go fast. Okay, let's talk a little bit about heterogeneous flops. So I talked about all these different kinds of compute that we have, and these all correspond to silicon on the chips. And what silicon you get depends on what chips you actually have. So here is another diagram comparing the various different architectures, because NVIDIA, has different market segments, right? So there's a data center segment, which is doing all of the deep learning server compute. And then there's also all the gamers, right? Who like buy NVIDIA, cards because they want to, have really nice graphics for whatever video games they're playing. And so an example of the consumer card series is the Turing series. And what you can see is that what you get on the Turing card is very different. And one thing I really want to point out is that, like, for example, you can do double precision compute on GPUs, but on the consumer cards, it's really, really bad because they really didn't put very much silicon for double precision compute in these cards. And we like one of the things I was like really interested in was there was from this community RLibM, which were these like very precise polynomial approximations for various transcendental functions. And I was like, wow, this will be cool. Can we like go ahead and put this in PyTorch? And then I was like, oh, but they're doing all of their compute in double precision, and we need to, have decent performance on Turing, and Turing doesn't have any FP64 cores, so I can't do this. Ugh. You'll notice on this other side of the table that there's a huge pile of tensor cores. What's a tensor core? Well, in deep learning, we're really big about matrix multiplies, and it's kind of difficult to like build silicon that can work for arbitrary floating point computation. So like tensor cores are basically special purpose silicon that is specifically for doing matrix multiplies. Basically, you get these like 4x4 blocks and you can multiply them together using a tensor core. And it's worth putting all of this onto the chip because, matrix multiplies are really computationally expensive. They do a lot of floating point operations per byte involved. And we'll talk more about this when we get to the memory bandwidth section. One other thing that I want to point out about this tensor core computation is that it actually is typically done in lower precision. In fact, you cannot do a floating point 32 matrix multiply using these tensor cores. You're always actually doing it in a lower precision. In fact, it's this weird alternate universe precision, which is not IEEE 32-bit floating point numbers. It's not IEEE 16-bit floating point numbers. Instead, it's this weird format that NVIDIA made up called TensorFloat 32. And essentially what they did was they were like, okay, well, we don't like that FP16 reduced the exponent size bits wise. So these diagrams are how many exponents versus mantissa bits were dedicated to each of the floating point formats. So we don't like getting rid of the exponent because that reduces your dynamic range on the computation in question. But we also need enough mantissa bits so that we can actually accumulate of decent accuracy. And we don't want to pay for 23 bits of mantissa. That's way too many bits of mantissa. So they're like, okay, we're going to just invent this new floating point format, and it's only going to show up inside the internal computation for the matrix multiply instructions. But then you get a bunch of people complaining that, hey, that's weird. How come my matrix multiplies are like losing, precision? Well, it's because, they were trying to save on silicon and they're using this interval format. And we actually, they asked us to turn it on by default, and we did for a bit. And then we turned it off by default because there were a bunch of people doing regular scientific compute. And they're like, hey, my matrix multiplies aren't working anymore. What's going on? Sorry, because, NVIDIA was like, it will converge with regular deep learning. We're not here. Let's talk a little bit about floating point FP8. So this is very new. This is coming with the H100 hardware, and there's so few bits, right? So I can actually like show you on a postcard every single possible floating point number in FP8 because there's only 256 of them. This one's only 128 because I don't need to show you the negatives. They're the same as the positives. Another weird thing they did was they're not IEEE compliant for the 4-bit exponent version, because they were like, we really want more dynamic range. So they got rid of all the nans except for one. And so you can go a little bit further here. So weird stuff, right? And why are they doing this kind of thing? Well, it's because of this other problem, which is the memory bandwidth problem, which is that when you're trying to make things go fast on GPUs, this diagram is the most important diagram, right? It says that, as you have a bunch of flops, there's some peak flops, which just corresponds to like the speed of light, like how much silicon you actually can do on the GPU in question. And then you have a problem, which is that you have some bandwidth available to you for actually reading things out from memory. So the more compute you do per byte you get from memory, the more utilization you get until you hit FPTalks, right? So as long as you're not actually doing enough compute on any given piece of computation, you are bandwidth bound. And this flips to compute bound only once you're actually doing enough, an arithmetically intense enough operation. I am so behind. So with memory bandwidth.
Yeah,
right,
Edward, we gotta wrap up.
Yeah, we gotta wrap up. Let me wrap up. Okay, so there's some stuff about memory bandwidth. I'm gonna wrap up. So let's see. So what do I want to convey to you, right? So the data size for deep learning compute makes tooling challenging, and we don't care that much about accuracy, but we care a lot about like reducing the size of our computations via quantization or sparsity or low precision. So, very interesting, different universe. And I'm gonna do questions. Thanks.
Thank you so much, Edward. Very, very cool talk, and I know that the short format of FPTalks is a big challenge for speakers. So we probably have time for one question, and I'm just going to pick one from the chat. Sam, do you want to ask your question? Do you want to unmute and ask directly?
Yeah. So good talk. And really nice. From the hardware perspective, people, what are you pushing NVIDIA to actually go and add to their GPUs? What is the massive missing bit? What would give you next performance up?
That's a good question. For the most part, we don't. How much can I say here? Okay, from like the open source framework developer perspective, NVIDIA looks at what the trends are for like what people are really interested in deep learning, and then they decide to put stuff into the chips, and then they tell us, hey, we're doing this on the next chip, and we're like, okay, we will modify our framework. So it's much more the other direction, where NVIDIA tries to like figure out what they want to do, and then they say, okay, you're getting this hardware in a year, and we're like, okay, well, we will make our frameworks work for this case. And sometimes they like make bad choices. And an example of this is like they added support for like 1-bit and 2-bit multiplications, and they got rid of it in the latest one because no one was using it. Like it just didn't get any framework uptake. So that's an interesting thing.
Okay, I can already see from the Slack that there's like 5 times as many questions as we can ask. But we also need to move on, and
I'll answer them on the Slack. So thanks for the questions.
Yeah, absolutely. And that's what the Slack is for. So our next speaker is Dolores, a PhD student from UC Davis studying correctness and tools to help people write correct floating point code. So excited for the talk. Dolores, do you want to start your talk?
Okay. Good. Okay. So hello everyone. My name is Dolores. I am a doctoral student at UC Davis. I hereby present our work with LNL about isolating the expressions that cause compiler-induced numerical inconsistencies in heterogeneous programs. So compiler-induced numerical inconsistencies are those that, because of the use of different compilers or aggressive compiler optimizations, the result of the computation comes out differently. One such inconsistency we have found during our research was that in the NAS parallel benchmarks in the FPTalks program, where, well, we could see that even though the inconsistencies for individual operations are usually just rounding errors, they can still build up. In this table, you can see that with Clang 03 fast math compared to MVCC 00, like they are already across compilers. Even when the runtime here is like we have like 100% speed up by using 03 and fast math, the maximum relative error in its output is 4 times larger. And this could be a problem in more serious usage situations, because in real-world applications, there are documented cases like the one in CSM, that's the Community Earth System model, where FMA instructions, merely like using FMA instructions, cause QA verification to fail on one supported platform. And these kind of issues took a lot of development time and effort to even locate, never mind like fixing them. Here are some common causes that we now know of that could cause compiler-induced inconsistencies, such as fast approximation or flush to zero. These are very common causes. We may partially disable optimizations or use higher precision across the board in our programs to resolve them, but it's temporary and usually much slower. So it is best if we can find out the cause of these inconsistencies automatically. We introduced our tool SEAL here, which stands for Compiler-Induced Inconsistency Expression Locator. It analyzes a heterogeneous program, usually containing CPU and CUDA source code. It generates AST and then starts iteratively isolating the code regions, as shown in the AST, that could cause inconsistencies to occur by traversing this AST. It uses precision enhancement, and then it uses differential testing to determine if we say enhancing a certain set of code will resolve the compiler-induced inconsistencies, so that our targeted code regions in the end will narrow down the targeted code regions. And in the end, we will have a minimal step of code that this statement, for example, would be the source of the inconsistencies. First, we talk about the hierarchy extraction module. It traverses through the program source code and generates this AST, grouping statements and basic blocks into a hierarchy. All the statement, basic blocks, and function nodes are organized into a tree, which the tree also keeps track of sibling and adjacency relationship between nodes. For example, basic block 4 and 5 are sibling nodes, and also like they are also adjacent nodes, and this will be useful later on. Next, I will show you how bisection search work. So because we need to isolate code, narrow it down the region of inconsistency further, we need to choose often, for example, in this case, between basic block 1 and 6, as shown in the graph here. So bisection search, what it does is it'll split code in two halves and then determine that if enhance the precision for either of them will resolve the inconsistency. In this example, we suppose we already know that the source of inconsistency is statement 6. So when we isolate basic block 1, we will resolve the inconsistency, but if we only enhance precision for basic block 6, it doesn't. So the search will then continue within the children of basic block 1 and discard the basic block 6 subtree. In the end, we'll see that statement 6 will be, in the end, finally be isolated. The time complexity in this case is O of our log n, where n is the number of total nodes in the AST. In another example, where suppose we already know that statement 6 and 9, when they act together as the cause of inconsistencies, then neither enhancing basic block 1 nor 6 would resolve it. So we keep both parts of code in our search, and we perform bisection search on children nodes of each part. And then when we perform both halves of the search, the AST, we will isolate statement 6 and 9. The time complexity, if in an absolute worst case, let's say if the inconsistency is dense, it will be O of n. Then next we use precision enhancement to approximate real numbers to avoid inconsistency inducing conditions and minimize rounding errors caused by inconsistencies. Compared to previous state-of-the-art, SEAL supports enhancing both CPU and GPU code. That's CUDA in this case. And it also supports enhancing just a single expression within a statement, which improves the usefulness in situations where in some programs, one statement could be very long and complex. The general idea of precision enhancement is shown in the two code regions here. Is that, let's say we enhance precision for both code regions, and within each, all floating point operations will be converted into enhanced precision as float to double here. And also at the beginning and the end of the region, we convert the variables to and from enhanced precision. Also, you notice that external function called like the trigonometry functions here are all converted to an enhanced precision version if we know such versions exist. Also, SEAL detects like redundant type conversions by performing a boundary check. If we look at the magenta region here, the variables comp and t, we know that they are converted back to float and then converted back to double. So this conversion is entirely not necessary, while it will lose some of the precision in the middle. So what we do is we SEAL detected and remove such redundant type conversions. And next we'll talk about how SEAL evaluates against state-of-the-art and also in heterogeneous programs itself. So to evaluate this, we use CPU and GPU benchmark programs. We have synthetic programs generated by Verity, and also real-world applications. And apart from that, we also evaluate our tool against the previous state-of-the-art, which is P-liner, as listed here, in all x64 benchmarks from its own evaluation. For the synthetic CUDA programs, we isolated inconsistencies in 328 out of 330. We have inspected some of these inconsistencies. We have inspected all of them. And we show you some of the cases here. For example, some normal numbers, when they are used, it could be flushed to 0. No, I would say treated as 0. And also using the compiler choose to use fast approximation operations, or sometimes it involves special values such as infinite. We also tested seal on inconsistency we have found or encountered on some GPU benchmark programs and real-world applications. To trigger the inconsistencies, we try to modify the error threshold, which is a previously like an existing method to try to trigger the inconsistencies. If you're interested, you can read the paper yourself. And we found 8 such cases as shown below. For these 8 programs and the inconsistencies, seal successfully isolates the statements shown here, and also subsequently the expressions as shown on the right that cause these inconsistencies, except one, which is the LU decomposition, where we only isolated the function that caused the inconsistency, which it contains about 10 lines of code. As for Cloud SC, which is an ECMWF cloud physics mini app, we have found the cause to be a floating point type conversion in a power function call. So we already notified the issue to developers and they have handled it on their end. Next, we compare seal against state-of-the-art, which is pliner. First, we use 50 synthetic CPU programs we already know they have inconsistencies on Intel CPU with the GCC compiler. Seal achieves overall better results than pliner as shown in the chart below. You see the orange bar represents seal and a higher bar represents a more finer grained isolation results. And seal performs like overwhelmingly better than pliner. Yeah. And next, we also tested seal against pliner in 3 NAS CPU benchmarks, and all of them achieves better, like either we achieve better, I would say isolation results as in CG.B, where we isolate the lines compared to only isolate a function of 160 lines of code. And also in cases like SP.8, both tools isolate different functions, but because this is because both are valid answers, they just pick different parts of the AST, which is also a possible scenario. So yeah, that's all from my end.
Okay.
That's it. Thank you.
Yeah, great. Thank you, Dolores. I think we probably have time for one question. Zach, do you want to ask yours?
How to unmute. Yeah, so I was super interested in the talk. One thing I was curious about is how should people who are the compiler authors use these inconsistencies to improve the compiler? It seems like a lot of these transformations most of the time are okay, but as you've shown, right, not always. So how do they work backwards from these issues to a compiler bench?
So one way that I can envision is that since we know which with the tool, we will know which expression caused the inconsistency. We can, like, as someone, like, as in my case, I would look at, for example, the IR generated by the compiler and or the binary. Like, you can clearly see, like in my examining, I could clearly see the difference between, for example, O0 or O3 with fast math, but also note that for a lot of these is, I would say, is intentional, like in fast math, because we have relaxed our standards a lot compared to IEEE. There will be cases like, oh, we do our compiler does reassociation with fast math, then this is like a side effect of reassociation. So with that, we can determine the cause, and then we can determine that if this is a bug of the compiler, or if this is intentional by enabling a certain flag. And with the flag it will come down to the software developer themselves to determine what would be the best, if we rewrite it, or if we rewrite the source code, or if we use, like, we don't use fast math. Yeah, that's it.
Okay, great. Well, there are more questions in the Slack, but
Okay,
I'm
yeah,
going to
yeah,
try to
I'll
move
try to
on to our
answer.
next speaker, and that is Edward Misbach. So Edward is a PhD student at the University of Washington, and he works both with Zach, who just asked the question, and also Steve Tanimoto on live programming environments. So Edward, you want to go ahead?
Just a moment. You got that. Great. Let me just go ahead and share my screen here.
Excellent.
Here. Great. So I'm Edward, and I'm here to present Odyssey, an interactive workbench for expert-driven floating point expression rewriting. So there are many excellent tools for floating point error analysis out there, and we all imagine experts working together with these tools to overcome issues in systems that use floating point. However, the reality is that sometimes tools are designed without consideration for the full scope of a user's needs, and then it can feel like the user has to fight against the tool or work unassisted when it comes to following their own workflow. Herbie is a tool that automatically rewrites floating point expressions and usually achieves very low error, as in the example here. This is great because it is fully automated and we can get an answer in about 20 seconds. However, Herbie's result here is incomplete. It's very good for most of the range, but still bad in one place. Human experts can also rewrite expressions. And it's frequently the case that they can outperform Herbie, finding less complicated expressions with no error. However, since this is not automated, it's slow, and there are only so many experts, and there are a lot of people writing floating point expressions out there. So we wonder, is there a way to get the best from both worlds? So let's look at what the user sees when they're using Herbie. They put in an expression, and then they get out a better expression. This is great in some cases. But if the output isn't quite good enough, there's nothing the user can do to advance using Herbie. So are we stuck? And the answer is no, because Herbie is not actually a one-shot tool. The truth is, under the hood, Herbie is essentially doing a graph search, where the nodes are expressions and edges are rewritings allowed by rewriting rules. From Herbie's perspective, there are many possible options. So it would be great if, by being a little bit less automated, we could give the user the same view of the problem. But how would that work exactly? Like, what is a good model for the way that this expert-driven exploration can occur? And this is the question that we want to address. So thinking about this leads us to the notion of a workbench. A workbench helps its operator to work on artifacts using a variety of tools. The tools may be automated or manual, but they serve clear roles. They visualize or alter what you are working on. And a big point of this is that the thing you're working on is external from the tools so that they can all take turns working together on it. So we started to imagine the system, Odyssey, as a workbench that would take over responsibility for managing the user's search and allow the user to leverage many kinds of floating point tools to navigate the space of expressions. And here we have a demo of the system we ultimately built to prototype this. And I apologize because I'm going to have to, oh, actually, I think I can share my sound as well. There we are.
We begin by entering
Hopefully
the
you all can hear
expression
that.
we want to write.
Great.
We can see feedback to make sure it is the right expression. We will optimize over the entire positive floating point range. After submitting, the interface updates. On the left, we see a table of rewritings. On the right, we see an error plot. We would like to diagnose which operations in the expression are causing error. There are two areas with high error. Clicking selects both the rewriting and a particular point. If we then scroll down, we can see the local error analysis for that point. For large values, the square root operation has a problem. Now we select a small value, and for small values, the log operation has a problem. Now let's generate some solutions. Let's start by trying to fix large values. As a human, we happen to know about hypot or hypotenuse, which is a special numerical function for accurately calculating the square root of two squares without overflow. We can already see that this is probably going to have better error. As expected, we have fixed large values. Now, for small values, let's try generating solutions with an automated tool, Herbie. There's an unavoidable pause here while Herbie processes a full rewriting request. In our paper, we describe how we exposed Herbie's internal functions as tools to avoid this delay for the other analysis operations. We now have our results. They are placed in the same table and act the same way as the other expressions that we wrote. They are sorted by average error. By clicking a result and scrolling down, we can see the full text of the result. If we scroll further down, we can see exactly how Herbie rewrote the program. For example, this is a Taylor expansion. Scrolling back up, we can see that Herbie had an idea about using log1p. A good expert would start thinking about rewriting using log1p at this point. However, for demonstration, we will instead focus our analysis on tuning an expression in this region which has some error. To do so, we update the input range. This resamples all inputs and reanalyzes all expressions on the new range. We are going to try to write an expression by hand which has less average error than the best one Herbie has given us. We first deselect some expressions to clean up what is displayed on the graph. We are planning to combine two different expressions using a conditional. First, we copy a branch from the left expression. Next, we mouse over the graph to find a decent branch point. Finally, we combine the left expression with the old hypot expression we want on the right. This gives us an expression with lower error than Herbie's best result. We can confirm that the mixed expression acts the way we are expecting by checking the graph. By exposing internal
Great. So in the remaining time, I'm going to talk about what we can all take away from this. I'll talk a little bit about what we learned from a user study that we performed in order to design Odyssey. I'll tell you how you can work with us if this sounds interesting, and I'll describe what we imagine future work looks like. In the demo you saw, something I want to draw your attention to is that it refers to a particular rewriting workflow, which is described here. Users diagnose errors, generate solutions, and then tune the ideas they come up with to their satisfaction. In our user study, this is the process we observed users using to solve rewriting problems, and we found it useful when designing Odyssey to refer to different steps in this workflow. The workflow gives tools clear roles and relationships. For example, the local error tree and the error plot play an important role in diagnosing error, and they work together. A broad lesson here is that applying HCI methods let us find out that there were sometimes big gaps between our hopes for what users would be able to do and what they were actually able to do with the tool, even when they were excited about using the tool. By acknowledging those gaps, we were able to build new tools to overcome them. For example, originally, users were having trouble figuring out where the error in an expression was, and we added the local error tree to solve that issue. So if you're interested, we are releasing version 1 at the end of this month. There's a link to the VS Code Marketplace here where you'll be able to find the application. As far as how we envision someone might be able to take advantage of this, Odyssey's architecture basically involves remote procedure calls to tools. As an example, in the newly released Herbie 2.0, we made some simple refactorings to Herbie that provide a useful HTTP API for Odyssey. In our paper, we say we turned Herbie inside out because we took useful internal functions like sampling and local error, calculation, and finding a set of many alternatives for an expression, and we made them externally available. So now any other tool that wants to can use that API or easily consume our data from it through Odyssey if it's embedded there. We're actually very interested in studying how we can make it as easy as possible to add more tools to Odyssey. So now we want to bring more users and tools on board to support more use cases. Incorporating output visualization, for example, is very important for this, and we had a couple of participants bring this up in interviews. People really want to know if they have an expression, does the error matter for their application? They want to pick a high error point and see whether that point corresponds to a reasonable input and whether the error is noticeable in real outputs. And this is just one example. Most of the participants we interviewed had ideas about other visualizations or tools they'd like to see added. In the classroom, we see low-hanging fruit around visualizing how floating point calculations work. So there's a ton of research on how interacting with visuals helps students build a mental model of a domain. And these tools that benefit novices also take cognitive burden off of experts by handling the fundamentals for them, as we think we saw with the local error visualization in our study. Finally, there's a lot of discussion about how LLMs will impact various aspects of research, and we wonder if an LLM could be a useful workshop assistant in this case. We already know that LLMs benefit from having access to real calculation tools, since they don't have to pretend to do math if they have a calculator. And we think that Odyssey might be an environment where there are many tools brought together, and there's a lot of data to sort through, and having an automated assistant might, in some cases, be useful. And if you don't trust the assistant, then Odyssey is also an environment where you can check its work against more rigorous tools. So in conclusion, we hope to continue helping experts work together with automated tools. And there's some links here to where you can find the extension to Odyssey and Herbie, and we plan to talk more about Odyssey at WIS 2023. So thank you.
Awesome. Thank you so much, Edward. Great talk. So we have a bunch of questions already in the Slack,
I can't hear.
Perhaps
we need audio.
Oh.
So I'll stop this.
Can you hear me now?
Yes. Yeah.
Okay. Maybe we should start with a question from Samir. Hello, Samir?
Oh, I thought it was already there. I'm curious about multivariables, multivariable expressions. So does Herbie/Odyssey work with 2 or more variables?
Yes, yeah. The way that we currently handle that is we'll show multiple graphs, essentially, one for each input. And so you can based on the input, you get a different layout of the error. And so you can see for like X or for Y or whatever, how the range of inputs goes. I think for many inputs, the number of sample points, I guess you have to think about how you set your ranges so that you get useful information for a particular input, but it definitely does handle multiple inputs.
So then you as a user must have some insight into where the troublesome area is so that you set the ranges correctly. So there is a risk that you run, which is if you're working with an expression that you don't have some intuitive sense of, that you may not have an idea of how to set which slice of the input space you should be looking at.
Yeah, I think that's an important consideration. Is what we try to do is we try to sample the input space uniformly, and hope that kind of hits some of you see some like spikes in places where there are error issues. And then that lets you kind of zoom down into those areas.
You can kind of gradient descent the error graph.
Yeah, exactly.
Thank you.
Okay, I think we have time for another question, and I'll use my privilege as host to ask it. So you mentioned at the end that there's that you hope to use this in like a classroom setting. Do you have any ideas or sort of preliminary like results on what kind of activities you'd want people to do in a classroom setting with Odyssey?
Yeah, I think just thinking about it, some things that I've thought about are that I think a lot of people know about things like overflow, but even in the course of our study, I was learning about things about other types of functions that have error like log. So I think it'd be useful to introduce students to the different types of error that functions can have, and to have them work through the process of given something like a quadratic formula or some very typical looking expression showing that we can find out where the error there is, and getting them more used to this idea that there's actually error all around them, and that they should be mindful of that when they're working with expressions.
Okay, yeah, great. So there are more questions in the Slack, but as always, we need to move on. I think this is often a whirlwind kind of aspect of FPTalks, but it means we get exposed to a lot of ideas per hour. So our next speaker is Ben Sherman. Ben was until somewhat recently at MIT, where he finished a computer science PhD with Mike Carbon. So he'll be talking about some of that work, which has continued a bit.
Thanks, Pavel. So I basically just want to show everyone like a fancy calculator that I made during my PhD. So hopefully this should be showing up.
Yep.
Cool. So it's like an embedded language within Haskell. So I'll just load it in and we can start playing at the REPL basically. It's also, I did not build out any syntax, so some syntax things will be awkward, and I'll point that out. But the basic principle is that everything in the language is a real number expression, like it means something that's a real number. And so when you want to look at it and you look at the answer, you just give it a precision to evaluate it to. So here, what I'm saying is, let's evaluate square root of 2. Let me just clean this up a little bit. Let's evaluate the square root of 2 to 2 decimals of precision. Basically, get me an answer within 1/100th. So it gives me an interval with a lower bound and an upper bound. And the guarantee, right, is that the true answer is between those bounds and that the bounds are going to be as tight as I requested. So the difference between the upper bound and the lower bound is 0.01. And so the nice thing about this is I can go back and I can get, since it's a real valued expression, I can get as many digits of precision as I want. Okay, cool. So that was square root of 2. Now you could imagine, right? We have our built-ins of like numbers, 2, square root. But how do you define square roots anyway? Well, the way you may remember, like, what is a square root? It's the thing that's such that if you square it, you get 2. So for square root of 2, right? And that actually gives you a method of computing it. It's like essentially just try to find the thing that's such that when you square it is 2. So that's like a root finding problem. And we know Newton's method is a popular and very efficient method for doing root finding. And so in this language, every expression is actually infinitely differentiable by default. And so we can create a new square root function. I'm going to do it right here. So I'm going to use this built-in function, which is a higher order function called cut root with bounds, which is just do Newton's method. So it says do Newton's method. I want some number between 0 and x. I know the square root of x is between 0 and x. And then I'm going to say, well, of what function? Root finding of what function? So find some function when it's equal to 0. And so what I'll just do is x minus y squared. So I'm just saying, find the y such that when I square it and subtract x, or subtract it from x, I get 0. So there's my definition. And now I can do that same thing that I did before with square root of 2, but I can use my square root of 2 function. And let's not go crazy here. And so I can compute square root of 2 like this. So the fun thing there is it's digging into that expression of x minus y squared, and it's computing a derivative to use Newton's method to get an answer that's fairly precise, and it propagates all those bounds within the language. So as I said, everything in the language is infinitely differentiable, which means there's a derivative operator just in the language, and I can use that on my square root method. So let's evaluate something's 2 digits of precision. Oh, and feel free to like jump in and ask questions live or ask me to compute something live. So let's do the derivative of my square root operator at 1. So we might remember from your calculus class, like this is like 1 divided by 2 square root x. And so at 1, it should be 1/2. And we see actually, it turns out here we get infinite precision. Here we get exactly, yes, the answer is 1/2. So you might wonder, like, Newton's method uses the value in the first derivative to get a value, right? But then how do we get the derivative of something computed using Newton's method, or the derivative of an expression that was computed using root finding? Well, this is just something from our calculus class. The implicit function theorem tells us exactly this, the derivative of an expression that was constructed using root finding. And that's built into that operator that we have, that root finding method. it's essentially everything in the language isn't just continuous such that we can kind of get arbitrary precision. It's also smooth such that we can take derivatives, and the higher order functions let us do these derivatives. So just to confirm that we can do this, we can even get the second derivative here. So just for the sake of time, I'm going to copy and paste and do this here. Now I'm just going to check questions. Is the requested accuracy absolute or relative? It's absolute. And so if everything is differentiable, there are no if statements or partial functions, or is there some weak derivative in use? So yeah, a lot of the paper that I have that's like related to this is about the handling of some of this partiality of like having things that are like continuous, but like only, differentiable, like not at a corner, but maybe it's like there's an interval derivative if it's a Lipschitz. So there is handling of that, but I don't want to focus on it because those are the not nice bits. And then like you just sort of pay a lot of attention to how not nice things get as you continue to take derivatives on stuff. So I'm going to just like stay in the smooth land for this talk. Cool. So we do the second derivative. It's -1/4, which maps with what I remember doing things symbolically in my calculus class. Nothing symbolic is happening here. It's really all sort of like more computational. All right, so I have an integral 0, 1 function built in that's doing like Riemannian integration, and that's a smooth operator too. It's a little inconvenient to have integral 0, 1, so I can build out a function that does an integral from a to b. And so I just have this up here, this my integral function, right? And it's just like use that integral 0 to 1, but like smush the inputs and go between a and b and then multiply the result by b minus a. So we can use that, and I can do things like using cosine, I can define sine. So I'll just do that. Oops. Here, so sine is the integral of cosine, right? So I can just do this. I'm saying integrate from 0 up to z, the function cosine x. And so let's just compute that we can do this. So sine of pi over 2, that should be 1, if I remember correctly. So I do it. Sine of pi over 2 should be okay. I must have done something wrong, can't figure it out here. Let's see, just check questions. What happens when you divide by 0? Good question. Let's see. Oops. Oops. You get an infinite loop. It just keeps trying to compute, because the thing is, if you do something divided by like this, right? Well, it's very quick, but it's sort of slow. It's very close to 0, and it is a legitimate answer. So it keeps trying to refine that 0 number, and it's an infinite loop. You could cut off here because it's like possible, but in general, it's uncomputable to cut off. So I just let it do the in general thing, which is an infinite loop. You can even do things like maximization. So there's a maximization operator in the language. So I can say, find the maximum value of this expression, choosing x's over 0 and 1 to like get this perimeter. I chose an expression that has a max of 1. And you can do argmaxes too, because argmaxes are just root finding, right, of smooth expressions. So I can say that where does the argmax occur of this thing? It happens at 0.5. So I'll just end off with like, this isn't super interesting, but it's like, take the derivative of the integral of a thing with like sine and cosine and log. And it's just one of these fun first examples that I found where like Wolfram alpha just completely barfs on this. It doesn't produce anything useful, but we can get an answer pretty quickly. So again, it's just kind of computing things through, but it's this language where all the operations kind of not only have like arbitrary precision calculation information, but smooth like all their derivatives, and it just all plays together nicely. So I didn't get into the time to say exactly how this works, but there is a paper which I should probably computable semantics for whatever.
We'll post it on the website.
Yeah.
Papers
Cool.
will be linked from the FP Talks website.
All right, so let's see. Let me just check the questions again. Does the argmax operator find the global maximum or just a local maximum? So argmax is finding a global maximum. So what it first does, basically, if I remember correctly, and you could implement it a few different ways, is it kind of checks all the intervals to see basically to find the thing that has the global max, and then it kicks off the root finding for the argmax. So if you have something where the argmax is not unique, you'll get an infinite loop.
Cool. And there's also a question from Paul Zimmerman. I don't know, Paul, do you want to ask it in person?
Yes. So my first question is My first question is what is underlying arithmetic package?
Basically MPFR, if I remember correctly. So I'm using a lot of operations from MPFR, and the implementation of sort of arbitrary precision floating point values, I think also comes from MPFR.
Okay. And when you ask a 2 digits precision, is it absolute or relative precision?
Absolute.
Okay. Thank you.
Okay, great. I think there's also a question in the channel from me, so why don't I just ask it directly? Oh, okay. Maybe I shouldn't take it up. There's a question from Benjamin Valby. Do you want to ask that in person? Maybe not. All right. So Benjamin asked. Oh,
there's a question in there.
Yeah.
I'm happy to just answer it. Yes,
Great.
it will give. The only thing it needs to do is give type bounds at least as tight as needed. So if we do, I think, was this the question? It gets actually infinitely precise answer, right? The difference between the bounds is 0 in that case. So of course that can only happen for rational numbers. Okay, so Sam asked, how is this different from Titanic, the FP core evaluator? Is there any MPFR under the hood? So yes, there is MPFR under the hood for a lot of the basic arithmetic. And I do not know what Titanic is.
I have a question. So there's when you say square root, the built-in one, not the one that you defined, or division, are those directly calling out to MPFR operators, or are those implemented as root finding as well?
Yeah, so the square root that I have built in is based on MPFR, which should be like the fastest version of that. It should be faster probably than this thing that's gonna like go through this language and use the root finding operator.
Cool. Okay, well, I think we're done just a minute or two ahead of time, which is perfect. The next thing up on our schedule is to take a half-hour break. But before we do that, I have a short announcement. Ben, do you think I can steal your steal your screen share? Yeah, so before we move into the break, I have a brief announcement / advertisement, which is that my student Ian Briggs is graduating soon. He's done a huge amount of work on numerics, libraries, function approximation, correctness, and he's worked with verification and synthesis and precision tuning. This is the first public announcement that he'll be graduating soon, and he's looking for a job somewhere in industry, ideally working on numerics. So if you have positions, ibriggs@cs.utah.edu. So please reach out to him. And other than that, let's take a half-hour break. I'll be around, but this is a good time to, refill your pot of coffee or whatever you need to do. And I'll see you all in a half hour to start our next session.
Okay. Oh.
All right, so we'll be starting again in like 8 or so minutes. David, I see you there, so glad everything is working.
Can you see me okay?
All right. Great, I can see your slides. All seems to be working. And we'll start in about 5 minutes.
Can you hear me?
I can hear you, it's a little quiet. Maybe it'll be fine. Do you want to try again? It might just be where you were looking.
Can you hear me okay?
Yeah, that sounds great. Excellent.
Okay, I'm ready whenever you want.
Yep, I'll just start at 10. I like to keep it on schedule. All right, so I guess our break is about over. So welcome everyone back to session 2 of FP Talks 2023. And to kick off our second session, we have David H. Bailey, who's a senior scientist, retired at Lawrence Berkeley National Labs, and he'll be talking about some new applications of using arbitrary precision at very high precision to learn some new things about Poisson polynomials. So please take it away.
Good, thank you. See, every conference needs a comic relief, so I guess that's me today. We will, whereas many of our discussions and papers and talks on floating point arithmetic are focused on 64-bit versus 32-bit versus 16-bit. Here, we're going to go very much the other direction to hundreds or in many cases, many thousands of digits of precision, which is required to get the results that we need. So basically, what does this come forward? Basically, this research arose from an observation back in 2013. We're looking at the Poisson potential function. In fact, a very simple instance of the Poisson potential function, which is shown here, this phi2 function. And just using numerical experiments, discovered that when x and y are rational numbers, then this phi2 function is 1 over pi times the log of an algebraic number. And so anyway, very interesting finding, certainly unexpected. And so with some initial computations, which were very difficult because this series converges very slowly, we were actually able to find a few instances of these algebraic numbers. So basically, a key breakthrough was in John Borwein found that, in fact, this phi2 function can be given by this expression, which, and notice these theta functions are given by series that converge very rapidly. Notice like they have like k squared in the numerator of that q constant. So these converge very rapidly, and it makes it possible to compute, like 10,000 digit accuracy, some of these phi2 functions. The other key tool here was the PSLQ integer relation algorithm. And interrelation algorithm is simply an algorithm that, given a vector x of real numbers, it returns integers a sub I, such that inner product is 0. And within the accuracy of the numerical precision that you're using. And the problem is that integer relation by any algorithm requires very high precision floating point arithmetic. So if we have an integer relation, say of length m, you've got to have at least m times the maximum size of the coefficients to have any hope of finding the relation, or otherwise the true relation will be lost in a sea of numerical artifacts. So anyway, efficient versions of PSLQ or other algorithms typically use multiple levels of precision, trying to do as much computation as possible with only normal double precision, and then shifting to higher precision as needed. So here's just an example. Let's suppose someone gave you this constant alpha, and they say we suspect it's an algebraic number of degree 8 or less. What do you do? Well, you just calculate the vector 1 alpha squared up to alpha to the 8th, and then apply PSLQ or some other integer relation algorithm. What you obtain is this vector, and that directly then is the coefficients of the polynomial satisfied by alpha. So basically, going back to this Poisson problem, here is the high-level algorithm we're using. We're given rationals, we guess of what the degree might be. Then we calculate this phi2 function using Borwehn's algorithm, and we calculate a number alpha, which, and you might wonder, why is that 8 in there? And it just turns out that the polynomials are simpler with the 8 there. But one way or another, we try to see if alpha is an algebraic number by using this PSLQ algorithm. If we don't get a result that's numerically significant, we try again with larger degree or with higher precision until we find something. If we do find something, we got to make sure that its result is irreducible. Anyway, here are some additional results from back in 2013. And these are very intriguing. For one thing, it raises the question, is that given some S, what is the degree of the resulting polynomial, at least for the case x equal y equal 1 over s? And I also noticed that when s is even, like 6, 8, or 10, that the polynomial is palindromic. In other words, the coefficients read the same backwards as forwards. And so does that pattern hold? In general, what's going on there? How are these algebraic numbers really connected to the rationals that we input? Anyway, these initial computations were very expensive. So help, we need more powerful tools. One initial result from the initial set of results was this Kimberley's formula. Kimberley was a postdoc or a graduate student at the University of Newcastle, and he just somehow divined this strange number theoretic rule, but it just seemed to match perfectly the initial results that we had. So anyway, it raises the question, does this formula hold for larger s? And also this palindromic property, does that still hold? Anyway, so 2016, it made some improvements to the software. For one thing, I used a new multi-precision package that I'd written, which can connect to the MPFR and GMP packages for underlying low-level operations to do the arbitrary precision arithmetic. And so anyway, with this new package, we were able to do computations easily up to like 50,000 digits. And here, for instance, is one result of when x equal y equal 1 over 25, if you can possibly read this very small font, here is a example of one of these polynomials. It starts out -1. It goes up to a maximum of about 10 to the 50th, and then back to 1 or -1 on the end. And so we might just add here is that this crescent shape is actually a very strong evidence that the computation was correct, because otherwise it is exceedingly unlikely that it would have such a very special and improbable form. This, with regard to these Poisson polynomials, here's an example. When I gave an initial presentation of these results, Nityamani, who was a student at Stanford University, pointed out the fact, which is clear in retrospect, that if alpha is the root of a palindromic polynomial, then alpha plus 1 over alpha is a root of a polynomial of only half the degree. And so because the cost of doing these integer relation operations increases very rapidly with degree, this resulted in a very massive savings of computer time when S is an even integer. Are we coming here? Okay. So anyway, with this new set of results in hand that we, like this one and others, this actually led by this to some actual results where we're actually able to prove the Kimberley's formula, at least in the special case, x equal 1 over s and y equal 1 over s. This actually turned out to be, we were doing some just Google searches on some of the coefficients that we had obtained. And this led to a paper by Savin and Quarfoot at University of Utah. And ultimately, again, then to a proof by Watson Ladd from UC Berkeley of the Kimberley formula. So again, this was a very nice conclusion of this initial phase of the study, but it still raises the question, well, what about all the cases where X and Y are not equal and where they're not just 1 over S? Is there a Kimberley formula for all of those cases? So again, we're back in we need a lot more powerful computational tools. We've got to do a lot more computing to explore all these other cases. So anyway, the latest instance of this software is an even faster package for doing the arbitrary precision arithmetic, which again can work either self-contained or can connect to the MPFR GMP packages. And then also put together a 4-level PSLQ algorithm that uses double precision, quad precision, then a medium multi-precision, typically say up to about 1,000 digits, and then the full multi-precision that can go up to 100,000 digits. And again, with the idea of doing as much computation in as low of precision as possible and shifting up only as needed. And so anyway, with this new tool, we ran up a total of over 2,200 cases, and including essentially all possible cases of P over S and Q over S, where S is up to 36. And again, we were using, at least for these cases, up to about 32,000 digit precision. And many CPU months of total computing. And the result is that we found that this Kimberley formula does not hold in this more general case, but that this modification that I list here does seem to hold in all cases tested. And it's basically Kimberley formula with a few exceptions and in one case, double Kimberley's formula. So again, this is and this generalized formula holds for again all of the 2,200 cases that computed. Anyway, here's just one very interesting fact that only came out with this much larger catalog of results in hand, is that many cases actually are sharing the same minimal polynomial. In other words, these are roots, distinct roots of the same minimal polynomial. So like all of these cases that I show here, 1/17, 117 up to 8/17, 8/17, all of those cases, their minimal polynomials is exactly this 64-degree polynomial that I show here. And there are many other cases of shared polynomials that I don't really understand very well yet. I mean, it's I wrote up a paper and included them all in tables, but I don't understand all of these cases of why all these polynomials are shared. Anyway, here, let me go. We go back to the very beginning here. You can see this phi2 function is this sum where over m and n that are odd. Well, there's a very similar instance of where m and n are even. And this is a psi2 function, at least in that initial 2013 paper. And indeed, as it turns out, that we also have this property that the psi2 function is given by 1 over pi times the log of an algebraic number. But these are very much more difficult to compute and to analyze. But just in the last week or two, I've actually had a breakthrough of sorts where I can now compute these. But we need much higher precision, and I've had to do calculations with 100,000 digit arithmetic to find these relations. But then again, this is a separate study. But if any of you are interested, I can tell you the details. So anyway, basically, by doing these very lengthy and very demanding computations with very high precision arithmetic, we've been able to find minimal polynomials for a very large catalog of cases. And although the original Kimberley formula does not hold in all these, a modification does. And although as yet there is no idea of how this might be proved. And we've also found this property of sharing of minimal polynomials that's at least at present very mysterious, but very, very clear. And essentially every set of rational study, we see these shared minimal polynomials. So this is all for the phi2 function. Well, what about higher dimensions? What about the when there are 3 arguments? Again, we can try doing that. We don't really have the equivalent of the Borwein algorithm for 3D. And this is going to take some really hard research to try to understand that. And then, just as I mentioned just in the previous slide, there's this psi2 function that finally just achieved a breakthrough, we can compute these, although it's very much more expensive than before. So that's my talk, and if any of you are interested and want to see the view graphs, you can go to my website. I posted it there, and also the full results in the paper of what we've done so far. Thank you.
Hey, thank you so much. That was a super cool talk. I'll MC some questions from the Slack, and maybe I'll start with a question from Samir. Do you want to ask it in person?
Oh, I'm curious what root finding algorithm you're using.
Again, we're not finding roots. We're going the other way. We're saying, given that we have a root, how do we find a polynomial?
Oh, okay. All right, thanks. Sorry, I misunderstood something.
Yeah.
And what's the advantage of using the PSLQ algorithm over something like LLL or another shortest vector algorithm?
Well, PSLQ is very much focused on the integer relation problem. LLL kind of has to be bent into shapes. And we have to make some assumptions. We have to convert the input data into a vector of integers. This requires some assumptions as to, anyway, I've tried both. I just find it's just easier to work with the PSLQ. But on the other hand, maybe some variant of PSLQ of LLL will turn out to be, say, much more suitable for parallel processing.
And what hardware resources are you using? Is it CPU only? Is it using GPU? How many cores is this running on?
My favorite platform for doing this has been an Apple Mac Studio. It has 10 cores, although the new one I have has 12 cores. And so I have tried with parallel implementations. The problem is that we've wrung out so much efficiency by doing these multiple levels of precision that there's not a lot of useful parallelism, unfortunately. Now, again, on the other hand, maybe some completely different approach to doing this will be highly suitable for parallel processing. I hope so. But, so for the time being, most of what I've done is simply multiple jobs running on multiple cores.
So I see there's a question in the Slack from Zach about picking the precision to use. You want to ask that in person?
Yeah, sure. So you've mentioned, and thanks again for the great talk, David. You just mentioned how this sort of iteratively increasing or increasing precision on demand is really helpful. I was wondering how your new library decides when to do that. Are you tracking intervals? Do you know something about the convergence rates of the computation? Like, what's the mechanism that lets you do that?
It's much easier, or at least much more straightforward. I just simply run it, and if we don't get with some assumed level of precision that's sort of projected from similar cases, we just run that, and if I don't get a numerically significant result, then I just try higher precision. And I keep jacking it up until we finally find a relation.
I see, because you can basically tell when the answer is well formed, and then you just double the precision until it comes back good.
Yeah, I mean, there's these when you find a detection, it's very clear cut. I mean, it's
right.
There's no mistake when you find one of these. You find you're looking at this one vector, and you look at it in its smallest value, and suddenly that drops, 3,000 orders of magnitude to machine epsilon. Well, that's a pretty good clue that you've got a relation. And yeah, I could try like intervals, but that would be hugely more expensive for a big arbitrary precision problem like this.
So I see that Ganesh has a hand up. So Ganesh, you want to go ahead?
Yeah. Hey, David. I was wondering whether GPUs or FPGAs would do the job better, because I don't think there's too much data movement, if I'm guessing it right.
There are, I have looked at that, but it right off, it didn't seem to work very well, quite frankly. But then again, I see that there has been, I did see a paper where someone had used a GPU as part of a arbitrary precision package. Seemed to work okay, not spectacularly well. But so again, it's possible. But so far I haven't found it very useful, unfortunately.
Thank you. Yeah.
I had another question to ask about some of what you presented. So you showed a bunch of results and you talked about some conjectures on bounds for the polynomial order. Are there any conjectures or bounds on the coefficients, or at least like their size? There's that nice sort of crescent shape. I imagine that could help pick the parameters for a run.
Well, you might say numerically, I see some general. I think the rule of thumb is that it's like 0.4 of the times the degree, but I've no idea how you could prove that. But it's, on the other hand, for this psi, this new psi function, the psi2 function, there it's not 0.4 times the degree, it's more like 10 times the degree. It's an enormously higher precision. And so yeah, I mean, you can just rule of thumb, but I just don't know of any way to make that rigorous.
Am I correct? If you had some bound on the polynomial degree and the coefficients, it would be possible to, if you had enough precision, to actually prove that the numbers to identify the algebraic number, right? There's some like minimal spacing of algebraic values.
Yeah, I've looked at that. It didn't seem very practical at the time at the present time. But yes, I mean that would be a very interesting to do, to actually numerically prove that that these minimal polynomials, that is the correct minimal polynomial for a given numerical value.
And the proof of the Kimberley criterion that you've done for the 1 over S case, that actually does, prove that these polynomials are algebraic and their degree, and that you found the right ones, right?
Yes. Well, to prove that the basic proof that they're algebraic, that was done back in that 2013 paper. But that didn't give any bound or inclination, any indication of the degree or the size of the coefficients. Kimberley's paper proved that that degree formula works, but again, not anything on the size of the coefficients.
Cool. Well, I shouldn't take all the time with my questions. There's one more question from Zach about the psi2 function, and that'll probably be the last question for this talk.
Oh yeah, I was just curious. You sort of teased that you had a new insight that allowed you to speed up the computation, and I was wondering if that was some kind of analog of what was it, the borrowing trick, or there's a completely different approach?
It's actually, there were some formulas in the original 2013 paper. I mean, I'd forgotten about them, went back and found it, but it turns out that the formulas that were given in the 2013 paper, there was a bug in the formula. And it's only after going through it and realizing that, then I was able to compute.
So revisiting was the key insight, like going back and making a careful, like combing back really carefully, and that
Exactly.
bug fixing. And I thought maintenance was only about testing and documentation, et cetera. I guess formulas need dusting off too. That makes sense.
Yes, indeed. Very good.
All right, thank you so much, David. Very cool talk. I think this is the highest precision we've ever had mentioned at an FP Talks before. I might have to go check the tapes on that, but I'm pretty confident that you hold the record.
Wait till next year.
That's right. That's right. You'll 10x your record. All right. So our next talk, we're going to switch gears completely. I guess this has been kind of a potpourri session. And our next talk is by Sam Coward. Sam wears two hats. He is studying for a PhD at Imperial College London, but he is also working at Intel on hardware design. And I think what we're going to see here is a bit of an intersection between these. So Sam, go ahead.
Okay, so hopefully everyone can see slides and all that to make some noise to come. But yeah, today we're going to be talking about how we came up with this new numerical hardware design methodology. This is very much methodology pitch, nothing really in practice. All the components exist, but we're sort of putting it together. But you know, as Pavel just introduced, I've got my Intel hat where I work on CPU design, and I've got my kind of researchy hat where I work on automatic data path optimization. And so what we deal with in graphics hardware is generating hardware that produces correct results, where correct is purely just, does it look okay on your screen? A lot of the time, a lot of our specs are much more flimsy than you have in CPU world. None of the IEEE stuff applies anymore. And so the reality is that our specifications are often, you know, natural language, no number formats. We generate non-bit accuracy models, and then we have to generate some really optimized RTL that maybe does something similar to what the C++ model does, but actually might do something entirely different. So the algorithm which we've been playing with as a group, so a numerical hardware group led by Theo Drain, is looking at this, basically generating approximate eigenvalues. And we've got a ton of different choices, like what components to use, what precision to use, what accuracies. And you know, we've been working on this for actually years. And so basically, when we look at this spectrum, you can do things at this top level of optimizing your algorithm, optimizing your architecture, all the way down to doing RTL level optimizations and bit level optimizations. And the reality of hardware design is that the pyramid is completely inverted with respect to how quickly we make changes. You know, bit level changes happen super fast. We change our logic synthesis algorithm, change the components there, and this happens really fast. But then the algorithmic changes happen way slower because it has so many massive.
My bad, I just accidentally muted you. I was trying to mute someone else.
No problem. But Bill says PhD in programming languages has been kind of pushing down from this top of the stack, whilst I've been pushing down up from the bottom of the stack. And so Theo basically said, can the two of us meet in the middle? And can we specify, simulate, implement, and optimize loads of different designs within a single day, looking at this full stack, rather than just looking at one component of it? And so basically we have all these problems, you know, to actually specify this. We've got floats, fixed integers, precisions, and we also want to be able to execute. So this is kind of related to the work that has been done with the ARM specification about how you can do machine readable specs. And people are exploring that a lot these days. So maybe I'll quickly flash over FP Core as what we came up with as from Bill, bringing that into Intel as a good way to do these numerical specifications. And they're obviously executable with using some of the different techniques we've got. But what's really nice is you have all these precision annotations. So you've got these float annotations, as you can see down the bottom left here. And we have loads of different choices about how we can implement different components. So here we've got trying to implement A times B plus C plus D. And you know, there's loads of different ways in which we can implement this. And at each of these different components that we could possibly build, we've got precision choices. So you can see the design space is massive, disaster, really hard to understand where to put your precision and how to actually tune these components, how to even select the components. Just more on the precision annotations, but hopefully this is familiar to a lot of people who've looked at FP Core before. So thankfully, we had already an FP Core simulator such that we could go and chuck in a load of different designs using MPFR as a backend. We can actually go and figure out what is the result being produced by these things. From those results and from the simulator, we were actually able to go and build real application level visualizations. So this is just an ellipse plotter, because basically we're looking at how do we generate ellipses in this graphics algorithm. And you can see as we change the proposed precision, so we have this blue ellipse representing our sort of current implementation. As we increase the precision, we do get closer to that green ellipse, the golden reference model. So that's kind of exactly what we wanted. But also we have a ton of choices. Well, we have all these precision choices. So what this allows us to do is put these precision annotations in and run a different ton of simulations to actually generate how is this the correctness in proportion to maybe some notion of hardware cost. And like all good academics, we chose the sum of all precisions to be, so this is basically the total number of bits to be our ridiculous hardware cost metric. But actually you can see it correlates quite nicely. You know, as you increase precision, sure, it does look like we're getting more accurate. One thing we did notice is that we can detect numerical instability using these techniques, like inherent numerical stability, because even as you're adding hundreds of extra bits, we can see that. So this actually goes up to 16 bits of total output, and we can never get past 10 bits of output precision. Even as we're adding hundreds of extra bits, we get no extra precision beyond 10 bits. We can't get to a full 16 bits. So what we actually detected that was that, you know, there's inherent numerical instability in this algorithm. And so we were able to refine that algorithm and generate this right-hand plot where we do get this nice frontier emerging. I think this is of the order of 100,000 points. You can see the frontier emerges pretty quickly as we simulate these different points. So having done all that, we built this compiler, built this compiler with Brett that looked at how can we take FP Core and generate bit accurate C++ models, because this is what we actually need to go and put into our simulation frameworks and into all of our downstream tools, all sorts of things. So you'll see we get some horrible templatized C++. So we take this FP Core on the left and generate some quite scary looking C++, but it targets this library that Bill and Brett have built up, that then you can map these arbitrary precision computations into arbitrary precision C++. In addition to that, they actually worked on generating ASL, which is an architecture specification language, which is related to or being brought over by Alistair Reed as similar to the ARM specification language. And also we can look at how can we generate multiple different outputs. So having built the compiler, it's relatively easy to then go and map that into lots of different target outputs. But this is where we kind of see a problem from a hardware perspective. We have this sort of infinitely precise specification where we can choose any arbitrary precisions. And then we need to generate some reasonable bit widths for our C++ model. And then we need to generate actually some optimized hardware where, you know, we're not using reasonable bit widths. We want to use the smallest possible bit widths in our final generated hardware, because bits correspond to area and delay in general. And so this is where we think we can use things like HLS to actually generate at least some reasonable performance hardware to give us some estimates early on in the feedback in the design cycle. We can get some estimates of how much area, how many cycles this thing is going to cost. But what the problem is that HLS, at least in the graphics domains, doesn't really achieve the desired power, performance, and area that we require if we're going to go and implement this stuff. And so this is where some of my work has come into this, which is about how do we take and optimize numerical hardware designs. And so, as you can see, we've taken this thing on the left, which is a very kind of simple floating point adder code where you're doing some addition, you're doing some renormalization, and then you're just truncating the output. And you can see going from the left to the right, the number of bits we're using drops from like 277 down to 25. And basically, we decided that competitive data path design is pretty much doing some value range analysis and rewriting and constraints. And so that's where we built this rover tool that basically takes in some initial RTL, does value range analysis and eGraph rewriting, which I won't necessarily spend too much time on today. But it's able to go and explore this massive design space of equivalent implementations of hardware designs, and then extract from that design space it's explored different area delay trade-offs within the single hardware. It also produces a formal verification flow where we can generate a load of intermediate steps, basically like a translation validation technique you'll find in compiler design. It kind of works, which is nice. So we see that it can take a simple floating point add or floating point subtractor design and generate something that is 33% faster and 41% smaller. So in a relatively large amount of time, because this is more towards super optimization, but in general, in hardware world, we're willing to spend a bit more time on super optimization. So this is what Theo believes to be a one-day operation. So one person writing your FP core at the front end, where we're generating some application level visibilities, doing your precision tuning using the simulation method we described, generating a C++ model that can then be fed into your simulation tools or into other flows down the line. That can also be shared with the system C. And finally, passing it on to Rover to generate your optimized hardware. What's nice about this flow is that you're getting this feedback at each stage of your design process, rather than, some architect giving us some specification all the way down to the hardware designers, where there's no real interaction going on. We don't really have any idea of how this is going to look. It's a bit difficult to schedule, difficult to plan. One thing that really doesn't exist at all at the moment is this interaction between IFP and Rover. So what should that passing of information be? Classic compiler stuff. How do you best communicate your intent from the left-hand side of this graph all the way over to the right-hand side in hardware design language? So that is left open. Maybe there should be some shared IR. Maybe MLIR has some insights for us there. So yeah, thank you very much. Any questions?
Very cool, Sam. Very cool work. Just before I get to anyone else's questions, since I can do that, how many different circuits or whatever have formulas have you used this kind of pipeline on? At least if you can share. Do you have some estimate? Is it like a couple? This is a work in progress, or is this being used pretty widely?
We're basically doing this for the first time in this coming 6 months or something, or 3 months. So we're midway through the process, probably somewhere at the halfway stage of doing this for that graphics algorithm we described at the start.
Cool. So I see there's a question from Zach. You want to take the first one, other than mine?
Yeah, sure. Okay, so Sam, I guess there's a couple of things I was curious about. One is there's different cost functions being used in different phases. So the precision tuning cost function uses this kind of bit cost metric, and the rover optimization is using more PPA. Presumably there's some relationship or interaction between these cost functions. I don't know, is that explored? Do you have any advice for when you have this sort of multi-phase pipeline, how to make the cost functions play nice together?
Definitely not explored. Only what we can say is that when Bill looked at how does this dummy silly cost of adding up all the bits compare to the metrics you were generating from high-level synthesis, actually they tallied up relatively closely. The same trends were emerging. Sure, you maybe weren't making an optimal choice, but you weren't making necessarily a disastrous choice, I think is what we can suggest. But of course, there should be actually backward arrows going on in this flow, right? If you want to go all the way back, actually the hardware, really this is a one-way line, but we should have these backward arrows telling us, from the hardware design perspective, actually making this precision choice here prevented us from doing optimization X, Y, Z. Maybe if we increase the precision, we can actually do further optimization. So there's a trade-off between squeezing your bit width down as much as you possibly can, and actually then preventing your compiler down the line doing a load of stuff.
Yeah.
But because we've got this full flow, that really we can have that backward arrow.
I mean, I guess also with those intermediate visualizations, you're still enabling people to do that. right? Like when it's, this kind of gets to the other question I had, which is how important is it for each of these phases to be predictable in terms of like being a, automatic search versus maybe a compilation where like, I know how to control what comes out the next stage of the pipeline by, tweaking what I put in.
I mean, from a user perspective, you want to know. So one of the things we really suffer from in like logic synthesis, I made my design better. I removed some gates, but actually the generated circuit got worse, and that's the most upsetting thing for a designer. So we always want to have, if some notion of yes, the designer clearly thinks this is better, that should feed through into what we see in our visualizations. If that visualization gets better, then we should be seeing that accuracy improve. So I think it's tallying that up, which is a bit of a vague answer, but yes. I think monotonicity is hard because there's also a lot of other tools going on in the flow here, which we don't have control over. So like the HLS tools are all closed source, the logic synthesis tools are all closed source. So maintaining that relationship through is not trivial.
Right.
Okay, so there are more questions in the Slack, both from me and others. But I think we should move on to the last talk of this session, which is going to be Martin. Martin, are you here?
Hey,
hello?
My computer thinks that you can hear and see me.
We can hear you. There's a bit of a buzz, but I think that'll be okay. It seems to have just gone away.
Okay, let me just try and share some slides with you. Cool. I know, I mean, it looks good for me. Does it look good for anyone else?
Looks good. Yeah, so Martin is one of the key developers in the CBC project. He actually gave a talk at one of the community meetings, I think a bit over a year ago, which is very cool. And today he'll tell us a bit about verifying programs with trigonometry in them. Go ahead.
Yeah, so David said that he was the comedy relief. I think maybe actually, I don't want to try and one-up him on that, but I think I might be, because I'm probably going to tell you about what doesn't work. So things that might work. I've got a finite state transducer and I want to prove some things about it. Okay, well that sounds potentially doable. It's got a finite input language. Okay, again, this is good. 2 to the 32 input letters. I mean, means you've got to do something symbolic, but this feels tractable. Total state, 128-bit. Like, this really feels like the kind of thing that we should be able to deal with. We've got some good sat solvers. Yeah, so let's have a look at my transducer. Oh, yeah. So this is actually from the wonderful C-Sound project. This is one of their audio filters. And we've got a lot of floating point stuff here, but we've also got trig functions. We've got cos of the angle. And we've got power, and we've got sine. Okay. So how could we do something about that? So I was at Oxford for a while, so I asked Daniel, and he says, oh, look, simple. Just inline the library implementation, feed the lot through CVMC, it'll be fine. Yeah, so I'm sure you lot know, but the modern trig implementations, the cost and the complexity involved really start to rise. You can write a very bad and simple trig implementation, but the more accurate you want it to be, the more expensive it is. Not necessarily just in terms of runtime, but also in terms of the complexity of the system. And generally, they're done by sort of reducing your input mod pi or pi by 2 or pi by 4, compute an approximation, and then construct the result. So okay, let's look at that. So the reduction. cool, it's just a remainder. Right, how many digits of pi do we do the remainder with? Well, that depends on how many bits you want out and how many bits will cancel out. Okay, how many bits cancel out? Good question. Turns out there's a wonderful, wonderful continued fraction algorithm for this. And this gives some surprising results. In single precision, the top line here is the number closest to pi. And that gives you an error about machine epsilon, okay? However, once you get further down, there's a number here which is about 500 and something, is actually quite a lot closer to a multiple of pi. And the same holds true with double, except in double, you've got a number that's, I don't know, about 100. So these are very much numbers that would actually turn up in a computation. And this is the point where I'm just going to be mean, because I'm doing this then with the x87 unit, and famously, if you try and take you do range reduction on the x87 unit, well, it only uses 68 bits of precision for the pi, so it will truncate your answer. The correct answers are at the top. However, it's actually quite a lot worse than that, because working through this continued fraction method, you find that there are some inputs like this one here, which are, I make that out by a factor of 2 to the 58. And yeah, so if we're going to compute these kind of things correctly, we're certainly going to need more than a 68-digit number. In fact, we're probably going to need to do our range reduction. I mean, at least twice the number of significant bits. And for those of you who've used CVC5 or any of the other SMT solvers, doing a very high precision modulo is already expensive. Oh, and then there's the polynomial approximations. And then there's the multi-precision arithmetic, because most of the implementations that Daniel said, oh, just use one of those. Well, because they're designed for actual hardware we have, they don't have easy access to doing a remainder in, 164 bits or something. So you get constructs like this. And it gets worse, because your range reduction produces an interval, because it's mod pi. And then your polynomial also produces an interval, because it's only an approximation. And what if that interval straddles a rounding boundary? Well, what do we do? Well, we could do it in even higher precision. And, at some point, you just got to stop. Current program verification tools, current SMT solvers, automated reasoning tools, they can't handle trig libraries as are written for use in libc, this kind of thing. And to be honest, I don't think anyone's going to fix it. I think the world probably only has a handful of people who might feel inclined to fix it, and I think I've talked to many of them, and they've all just gone, hell no, we're not doing that, not unless someone pays a vast amount of money. Okay, so if we want to reason about our code that uses trigonometry, we can't just take the actual code that gets run. Okay, so who else could we ask? We've asked Daniel. Let's ask Tony Hoare. And it says, well, it's simple, you know, pre and post conditions. So this is the classic deductive verification approach. You write precondition, which for most of the library functions to be empty. You write a post condition which says, well, what gets returned meets this formula. And then you can use that pair instead of the implementation of the trig function. Great. So what should the post conditions say? So this is a quote from the C standard. This is the 99 edition. The more recent ones aren't any better. And it's this fantastic thing. The accuracy of floating point operations at the library functions that return floating point results isn't implementation defined. The implementation may state the accuracy is unknown, which, you know, Sam was just talking about informal specs. I mean, I think this is quite an informal spec. And the terrifying thing is that if you look at other language specs, this is actually good, right? Most languages just don't even talk about how precise must your math functions be. Paul Zimmerman, various of his team have been working on actually trying to see how bad it is in the real world. And so here we have a whole bunch of different math library implementations of functions and the maximum errors. If you want to know more about this, ask Paul, it's his work. But the point here is that almost all of the implementations people are currently using do not return the correct result. They're normally within what maybe wrongly rounded or maybe one ULP, but okay, how are we going to formalize this? And then you start thinking about, okay, right, well, we'll just write some maths to describe what it does. And you start trying to do this and you realize that if you know, a function which is sort of the perfect sign, you take a floating point number, you turn it to a real, you compute the sign, and you turn it back to a float. Okay, yeah, it's got some really wonky properties. So about 75% of the inputs, it's linear. Because once you get to, there's a lot of very small floats, and they are basically x cubed over 6 is very, very, very small. Also, once you go over about 2 to the 27, so this is another 40% of floats, the sign just kind of oscillates chaotically, and obviously it depends what you're trying to verify about your system, but if you know, are we honestly saying your control system is safe because it happens to follow the exact chaotic iteration of the sign? It doesn't work for me. Yeah, so again, I can't see that there is an accurate and reasonably performing way of writing a post condition for what an actual sign implementation does. So, well, what could we do? And at this point, genuinely, I would love to hear other people's ideas. I would love to hear other suggestions. Okay, so maybe people are going to save us. I noticed that we've got several talks on correctly rounded high-performance math libraries coming up. I'm really excited by those because that might actually mean that we've got a sensible spec to implement. I think, you know, we can leverage these kind of bizarre behaviors to kind of do multi-levels of specification. so we can write, well, for small values, you just return X, F, the input. Slightly larger values, it's basically that, or, 1 ULP out. The larger ones, for actually a surprisingly large number of things, just a stupid approximation like x minus x cubed over 6 actually works well enough. And for the high ones, so I think it might be possible to generate a series of these specifications, starting with the cheap, simple ones. Yeah, it might also be possible to build a version of the CVC prover that can really reason with mixed float and real problems. I think it's doable, but it seems to require some bizarre result about the existence of epsilon balls within the cells of a cylindrical algebraic decomposition, something like that. And yeah, so I believe someone can do it. I just don't know if it's me. So what are we going to do? How on earth are we going to verify code that uses trigonometry? Inline the implementation and fix the solver. I just can't see it happening. Write a pre and post condition. No, not seeing it happening. Really support all the people building correctly rounded implementations. Tell all of our users we're only going to do correctly rounded implementations, and if you want to verify code with a non-correctly rounded trig implementation, then you're wrong. And maybe get this into an SMT solver. I don't know. So thank you very much for your time and attention. And I would love to hear from some people who could help me with this one, because yeah, I mean, I've been trying to solve this for a few years, and the best I've got is a talk full of things that don't work. Anyway, I think I'm over time now, so I'll stop.
All right, thank you so much, Martin. We are a bit over time, so I'm gonna cut the Q&A short, but there are a couple of questions in the Slack, so you can attend to those during the break. I think we're at the end of session 2, and as Martin previewed a little bit, we're gonna have actually quite a few talks on correctly rounded math libraries in the 3rd session. So we're gonna take a half-hour break. I'll see you all back here after you all make another pot of tea or have lunch or whatever it is you're gonna do during the break, and then we'll be back for session number 3. And Mark, I'm gonna kick you out of screen sharing if I could. Or maybe if you could unshare. Yeah, perfect.
Okay, now that we're officially in the break, Martin, I had a quick question, because I feel like if you're still online, maybe you've stepped away. Are you there?
Yep, I'm here.
I feel like the SMT community has a solution to this, although it's somewhat indirect, which is whenever there's a new domain or theory and nobody quite knows the right way to tackle it, you make a benchmark suite and you put it in SMT comp, and then you wait a few years to see, like where things shake out. And I think part of that is that a lot of times those come from the use cases people have in mind, and that helps people focus on like how many programs can CVC verify by just knowing like the intervals of sine, cos, tan, and whatever, right? Like,
can I answer this in the form of a joke?
Yes, please do.
So,
I insist.
So, a man goes to the doctor, and he says, "Doctor, I grew weary of this life. All my woes weigh me down. I just can't see any joy or happiness in the world. And the doctor says, I have a solution for you. Last night I saw the great clown Grimaldi, and he gave such an amazing show. It's lifted my spirits. He is so funny. And the man says to the doctor, yes, but doctor, I am the clown Grimaldi.
Right.
Yeah. So in the SMT sense, I guess I'm normally on the other side, receiving the sets of benchmarks and then trying to do something with them.
Right.
But yeah, I mean, like, maybe we need to take some of the FP core benchmarks and just sort of see what's going on, how much is there. There is some exciting work. So CVC5 does have real value trig functions, which produce correct answers, but are done through a bunch of linearization things. Maybe we could use those. There are people pushing for a new theory, TNA, transcendental nonlinear arithmetic. Yeah, it's not a stupid idea at all.
Yeah, but I mean, your point's well taken, which is that somebody's going to have to do something with it. I guess what I was thinking is maybe it's a way to start getting figuring out how to subset the problem to chip away at it.
Yeah.
Rather than boil the ocean, get full support in CVC for trig. Like that seems hard, but if you just need to track intervals really nice, maybe that gets 90% of what people want to do. I'm not sure.
I also want to just advertise my own project and say we would love to have some verification tasks in FP Bench as well. So if you have specific problems, we'd be happy to host those. And I'm sure they'd be useful for people working on error bounds or something like that as well.
Yeah. Should probably try. So the C-Sound project that I got my initial example from, they've got a load of these kind of like digital filters, and they go from the very, very simple up to some really quite sophisticated things. And there are a bunch of questions they want to know answers to, things like, well, what's the maximum gain on this filter? Which feel like they should be simple to answer. But they're not.
Yeah. Well, in particular, they don't want to know the maximum real gain. They want to know the maximum floating point gain. Or they want to know, I see.
Yeah,
so
they want to
implementation do.
What does the implementation do? Because there are some really weird things in some of the digital filters where it's like, oh, well, we put this in to avoid this particular problem, and the solution works perfectly for the reals. It's just in a few cases it doesn't work in floating point.
This is like the Tom 7 training with rounding error stunt. Yeah.
So yeah.
I think it's you ask an interesting question, like the extent to which real number identities could even be true for floating point. I mean, you have the example of like sine of x plus 2 pi. Does it actually work? And I guess it doesn't work due to rounding error.
It doesn't work exactly due to rounding error. It doesn't work for large numbers because at a certain point adding 1 pi doesn't, you then probably round it back off.
Right.
Even for fairly small numbers, it doesn't really work because of the noise you generate when you do the range reduction. So basically, you can't do any of the kind of trig rewriting things you'd like to do. Just don't really work. There's also some other oddities that is probably well known to this crowd, but surprised me. So things like if you were trying to write a model of what tan does, you're like, oh well, it could generate infinities. Apparently it doesn't.
Right. There's no floating point input where it returns infinity.
Yeah, there's actually quite in floating point terms, quite a low upper bound on what it generates.
Yeah.
Which is mad. Sine only has like 2 zeros, which is plus and minus 0 because nothing else is quite close enough to a multiple.
Right.
Yeah, it's just.
Do you know if sine squared plus cosine squared is equal to 1 in floating point? That seems like one that potentially could be true.
It's near, if you're using small enough values, it's near enough true. Like it's within a couple of ULP. Yeah, it falls in the category of nearly.
So are these identities actually useful to the solver? Can it leverage these? Like if they were true, which they're not.
Yeah, if they were true, then potentially yes. So most, again, forgive me, people probably know this, but most SMT solvers have quite a substantial rewrite system in them. And each individual rewrite feels like it doesn't add very much, but the sheer weight of them, kind of like waves in the beach against the shore, enough waves, you've got a problem. So yeah, it would be nice to be able to do that, but yeah, it just doesn't really work.
Yeah, cool. I mean, one of the things my student Ian, who I advertised earlier, has been working on is math function implementations, and we have not thought at all about implementing math functions for verifiability.
Yeah, there's loads of really cool work on proving that your math function is correctly implemented.
Right.
But yeah, if you want to create a kind of solver-friendly math implementation, that's a whole different game. I think I know some of how to do it, but yeah, it's kind of wild. It's just different kinds of algorithms.
Yeah, well, it's a whole different set of constraints, right? Like solver friendly versus what you normally care about, which is like accuracy and precision.
Yeah. So maybe at some point I got to write one of those.
Yeah. Yeah, very cool talk. Right. So there's some interest in doing like a nonlinear transcendental arithmetic in SMT.
Yeah, so CVC5 is just so the problem with TNA is that as soon as you put trig functions in to the reals, you can create pseudo integers.
Right.
And that means it's undecidable.
Right. I think with isn't it the case if you just add the exponential function, then actually it's unknown whether it's decidable or not for reals specifically.
Yeah. There's a few of these like, oh, but if you use this with this restriction, then it is. It's right on the boundary. And yeah, so CVC5 has support for some trig functions. The MathSat team, trig functions on reals, my problems with them are floats. The MathSat team have done some work on getting trig functions working there, and they seem to be doing something a bit deeper. But yeah, I mean, people would love it. It's just hard.
Yeah.
And having like made a horrible joke earlier, there is also like a bit of a chicken and egg problem in that if there are no solvers that handle TNA, then there aren't any problems, because why would you generate them? Because you can't solve them. But if there aren't any problems, it's hard to, it's hard to work out, as I think it was Zach was saying, it's hard to work out where the effort should go. So yeah, if you have some fundamental problems, then definitely there are people who care.
So do solvers do internally some kind of like interval arithmetic or anything like that to like narrow the range of possible answers? Is it possible to like take some bounds information and feed that back into the solver to help it narrow the search space?
Some do. So Colibri, which is Francois Bobot and his co-author, whose name escapes me, is doing difference bounded matrices. So they're very, very interval-like. There's one of the floating point solvers in MathSat is also very, very heavily interval based. So yeah, having that kind of information would be great. Yeah, another issue with transcendental arithmetic is that what do you return when you say SAT? Because your answers may not have an easy or simple closed form in which you can actually say what satisfying instance is. So I have seen some work where people are doing kind of intervals, but using the intervals as a witness.
Oh, I see. You're saying the real value x that satisfies some equation, it might not be rational or even algebraic or anything like that. It could be just be some number that does something.
Yeah. And yeah, kind of trying to convince people of the satisfiability of something with like algebraic numbers. Like after a while, you can kind of convince people that you're not just cheating and telling them, oh, well, just work out the root of this. But when it's got trig functions as well.
Yeah, that's very cool. I remember for some of the work during my PhD, we were looking at doing trig computations exactly for the purposes of 3D printing, right? But that was leveraging the idea that you're only interested probably in like angles that are rational multiples of pi, right? So that you're only really doing computations with algebraic numbers. It was just finding like an efficient way to represent those.
So that actually that came up in the peanut gallery during David's talk. I don't know if you remember, Pavel, we would search for particular floating point constants to try to figure out what trig expression tended to evaluate to those, right? It's like,
yeah, Zach had a bunch of like failing test cases, but when a test case fails, the only thing you'd get out is like the floating point input that made it fail. And the computation was pretty big. So, you know, you'd have like a surface intersection, and they don't actually intersect, but but it says they intersect, and it says they intersect at this point. And we'd go back at that point, we'd stare at it and be like, well, if we subtract off 7√5, we get something that looks like a rational number. So, you know, maybe this number was actually such and such.
So there's been a couple of projects in the past to have like a floating point constant atlas, where you you put in a constant and it gives you a set of expressions that like small, interesting, reasonable expressions that evaluate to that constant. I think it could be a super fun service to run. It's kind of a goofy idea, but it's sure helpful with debugging.
I might add, this is David Bailey, that there has been a couple of those, but
yeah,
they've been taken down because it turns out they were security holds. And
security holes?
Yeah. And they just couldn't find a way to plug the security holes, and so they've been disabled.
So people were taking over the server by asking about strange constants, or?
Potentially could. In other words, it was requiring computation to be done on the server that was problematic.
Huh. I never would have imagined. That's wild.
Anyway, but that's the answer to your question. Where are these tools? I think maybe there's one that's still available. It's not that great, but I could check. Anyway, send me email. I'll tell you what the status is.
Definitely.
Yeah, I mean, I'm sort of thinking of the online encyclopedia integer sequences. You know, we shouldn't let them have all the fun.
Yeah, the online encyclopedia of floating point constants.
Well, the best thing is that the number of integer sequences is, unbounded, but there are only so many 64-bit floating point constants. And if we aim at 32-bit floating point constants, then we could potentially get expressions that generate all of them up to some depth.
Yeah, I mean, like, say, CVC5 has the kind of Cygus expression synthesis engine. Now, in principle, the floating point theory should work with that. We have actually used it a couple of times in anger, like serious things, and it did, with a little bit of poking, work.
Right, so synthesize an expression that evaluates to a specific floating point constant.
Yeah, I mean, so the original use was to, you kind of give it a, well, this is the expression, or here's a kind of black box. I want a function that evaluates, given.
Oh, I think Mark might have dropped. I remember he saying he was having some.
Kind of like the super optimization thing.
There you go. Yeah, I wonder if you could use that for debugging. You can imagine, you get a crash, and you rewind from the crash and just look up some of those floating point constants and see, what computations might have generated those floating point constants, and try to pattern match to the program itself.
And there's some relationship to like FP debug or herb grind or Santosh's posit debug stuff as well.
Yeah, I think the challenge is, what do you regard as kind of reasonable inputs? Because, for any given constant, I can always generate you the expression that, exponent 1 higher divided by 2. But presumably you don't want that. You kind of want the expression to be generated by things with relatively simple input values. Don't know.
Okay, so we're like seven minutes away from session 3. Tue, are you ready? Okay, great. We're not starting yet, but it's just checking in to make sure everything's working. Very excited for the talk, by the way. I don't know if you know this, but we've had like a kind of an ongoing, series of talks on the RLibM project. And I remember Jay giving the first talk like 3 years ago, and talking about this as like this very hypothetical thing. And it's cool to see it like year by year, the talks get more real and practical.
Yeah, the RLibM project is actually one of the people helped me to start up the this LLVM libc project.
Yeah, I think it's actually driven a lot of work. I mean, Paul Zimmerman's core math is another thing that's like really pushing this to, there's more and more papers now. After a long hiatus where not many people worked on math function implementation, it really seems like a big area right now.
Yeah, there's still a lot of work to be done, especially for higher than double precisions. But yeah, it's exciting.
Yeah. Well, my understanding is double precision is also not solved. Maybe Paul will reveal in his talk that actually he has solved it. But last I heard, as of 5 minutes ago, not to speak about what's going to happen in a half hour, my understanding was even double precision. It's not. We still don't always know the correctly rounded results.
Yeah, but at least I think the strategy in the paper that Paul published a while ago, that we make it as accurate as we can, and then maybe sending the signal out once the user able to find one that failed the final test of the accurate, and then make it a bounty.
Oh my goodness. Yeah, how many bugs do you think there will still be? Hopefully some pretty small number.
Yeah. So internally we do have the first testing going on for the 64 bits, but so far at least for the function that we have, it's not come up with anything yet.
Yeah, so 64 bits is just such a big space, right? With 32 bits, it's actually not too burdensome to say test every input. And with 64, I know you work at Google, but I think you still don't have enough compute to really know.
Yeah. Maybe next time, instead of computing pi to trillions of digits, we might propose to run one of the functions for 64 bits.
And make the atlas of floating point numbers that we were talking about.
Yes.
Yeah, great. Yeah, well, I'm very excited for the talk. Yep, great. Screen share works fine. Okay, well, I think I should at least start the introductions and get people back to their screens by talking loudly. So we are back for the third session of FP Talks 2023. And in this session, we'll see a lot on verification, correct rounding, and error bounds, which has always been a popular topic here at FP Talks. To kick the session off, I've got Tway Lies here. He's a software engineer at Google and more importantly on the LLVM project. And he's gonna be talking about maintaining the LLVM libm implementations. So Tway, please take it away.
Thank you, Pavel. And hello, everyone. So today, I'm going to give an introduction to the project that we have for about 2 years that we're implementing the libm inside LLVM libc. So first, so what is LLVM libc? This project started about I guess 3 years ago. It's to implement the libc inside the LLVM umbrella. And now we aim to be a drop-in replacement for the legacy libc on any platform. And and so we in our build system we have the overlay build mode, so that will allow you to slowly roll out function by function selectively. And the license of the library allow you to do the static linking and build from source for it. So everything is implemented in C++, just like most of the LLVM umbrella. And so we would like the code to make it look and feel like modern C++ library. So here's the homepage to the project and the GitHub link. So how about the math function in the LLVM libc project? So our goal is to implementing all the C99, and thanks to Paul, now we are aiming for the C23 math functions. And we may include other functions that outside the C standards, such as the reciprocal square root or the sine cosine. And we would aim to support for all the floating point format-ish in the C standard, single, double precisions, extended double, and quad precisions. And we support most of the platform that we're interested in, like Linux on x86, AR64, and the new platform RISC-V. On Windows, x86 64, and also the AR64 if the Windows on ARM fully materialized. And on Mac OS, we currently support on both Intel and AMD. Sorry, not AMD, Intel and M1. And currently there are efforts from AMD side to port the libc to the GPU, and they do have working examples for NVIDIA and AMD GPU. So Intel might need to have set up something on there. And there are also parallel effort to make this libc work on the bare metal use case especially for ARM32 and RISC-V 32. So for the status page of the math functions, here's the link. So our math functions library has two highest priority, and the first one is the accuracy. So when I started about 2 years ago, we have a discussions of what is the trade-off, how should we implement those functions between performance and accuracy. And in the end, we come up that in the first implementation, we should aim for as accurate as possible, because it's going to be much easier once people roll out to make things faster later than we make things more accurate but slower later. And people are going to be much harder to accept that. And so I reached out. At that time, I found out there are two current ongoing projects about implementing correctly routed math functions. They're the Core Math project and the RLibM project. And after reaching out to them, their work inspired me to make the requirement or make the goal to implement the libm to be correctly routed to all routing modes. Currently, we set and test for the 4 standard routing mode. But I know that, for example, on ARM, they have an extra one that we need to add and test if needed. And we do test the accuracy on most of the platform that we could, but some platform we might have to loosen the, for example, like the embedded system where they don't have enough memories to store the big tables, or for GPUs due to some code size or memories or performance, or even the FPU accuracy where they just completely drop off the normal part. And for the performance, we would like the libm to be usable in production, so it should be comparable to other accurate libm library, or mostly the GNU libc library. But we also need to avoid the pitfall of the IBM accurate math library, in which they have extremely high latency in the worst case. And for the performance purpose, we can totally utilize the platform-specific instructions whenever applicable, especially for newer platform turning up, like GPUs or the RISC-V. So why is accuracy important? So the correct routings will actually implies one of very important properties is consistency. If the math function output is consistent, is correct routing, it's going to be consistent across the platform and the library versions. And that will actually significantly reduce the toll when we update or integrating the libraries, or whenever a new glibc. So at Google, whenever the new glibc rollout is actually a big effort that takes months, because especially on the math side, because a lot of the golden files need to be updated, and it's spread across multiple teams. And to update them is it's just a lot of work, and it takes too long. So with the new functions that correctly routed function that we roll out in Google Productions, is we pay the first time cost for updating those tests when we roll out. But after that, all the iterations is actually extremely quick and effortless. So no more. Also, like, because the output is going to be identical across the platform, so no more if-def for switches in the golden test, and no more updates when we roll them out. And actually, any of the new performance improvement, as long as we can guarantee the accuracy, we can just immediately roll out without anyone notice, maybe from the except from the performance side. And moreover, now the golden test is not going to be a burden anymore. It might be the things to keep track of, so that you can make sure that the system or the algorithm is correct. It make it similar to integers golden test. So for our library, we implement in mostly in C++. Right now, they are I think they use C++ 17, and it's slightly different from other math library, because they are mostly implemented in C and a lot of assembly. So there are some nice things in C++. Is using the templates, and we can simplify a lot of macros. I think one of the hardest one when I was learning how glibc implementing math function is a lot of macros.
Tway, I think we're getting some bandwidth artifacts. I'm going to turn your video off to see if that helps.
Thanks. Let me. Is it better?
Yeah, I turned your video off, and hopefully it's going to be a little better.
Okay, thank you. And also, like, one of the hardest problem in in programming is naming. And so with C++, we are allowed to overload the function names and operators. So the number of names I have to come up with is a lot less. And also with namespaces to help to organize the code. So what did we utilize to implement the math functions? Is that there are a lot of recent advances in floating point arithmetics, especially in the worst case analysis, as a lot of people mentioned. So previously in the IBM accurate math library, I think the worst case, they bump it up to 800 bits. But now we know that a lot of math function can be in double precision, can be done with a lot less than 200 bits. And there are many tools to generate the polynomial approximations, like the Solias or the RLibM project. And there are many tools to analyze floating point errors from Kappa to SageMath. So also we intensively implement with the modern CPUs. They have fused multiply add and floating point routings or others extensions. there are many difficulties, of course, in implementing. So our libc is built from ground up, and there are a lot of building modes where we assume that no other libc, and so there are problems with circular dependency with the built-in compiler built-in, because some of the building modes, those floating point built-in actually make call back to the C library, and also managing the platform dependence on those, and also the problem with optimizations on the new platform that doesn't have the compiler built in yet, such as the RIX5 or the ARC64, if we don't rely on the built-in FMA. Also, the detecting routing modes for exceptional cases can be expensive. So how do we test, make sure that our library is correct? So we, at the first round, we have unit tests for exceptional cases and some hard to route inputs. And those are running on pre and post commits on the LVM project on all the supported platform. There are some platforms we are trying to turn up the bots. And we have the exhaustive test for all the single input, single precision math functions that is running. And right now it's running bihourly. And we have the first test for the rest to randomly generate and check against MPFR. Also, the core math projects, especially Paul and the RLM project, help us to independently verify the accuracy of our implementation. So next, I'm going to talk about how the performance of those functions that we implemented so far. So for the setup, we use Ryzen 5900 on Ubuntu and using Clang 15. And for the micro benchmark test suite, we use the performance test from the core math project, and we compare against the system library, which is the glibc version 235. So here's the throughput when we up the around almost 30 functions that we implemented. There are some double precisions function in there for the log functions, and the rest are single precisions. And we can see that the performance of most of the function is within the bound that I artificially set, is within 2x of the glibc implementation. So the blue line at 1 is the glibc, and the green part is the throughput compared with over glibc of using the FMA on x86-64. And there are a lot of functions that we are faster than glibc, and we are able to identify like 6 functions where glibc will need improvement because those are, we are about like 4 to 6 times higher throughput than glibc. And here's not only the throughput is good and better than glibc on average, the latency we are able to cutting down also, and especially on those 6 functions that I mentioned on the throughput, the latency is also very bad on glibc implementations. So those are, I think, the immediate part that can be taken. There are some spike on the red in here, which is where we don't use the routing and we don't use the FMA instructions. But I think those that can be fixed or improved. But right now, most of the CPUs on the x86-64 work, we have at least FMA AVX2. So that is not urgent. So in summary, compared to the glibc on x86-64 on our system, on average, the latency we reduced by 23%, with the maximum about 70% using FMA or SSE 4.2. The throughput, we more than doubled the throughput on average, and the best case, it can reach into like 5 to 6 times. We also help Paul to port the test bench to the performance test bench to ARM64, and we run them on various ARC64 devices, like from low power like Raspberry Pi or Raspbian 3 to the Cavium machine, which is the high performance ARM CPU, and we got similar improvement, but the number is not as big in here because so there are room for improvement. And so the latency improved is only like 1 to 2% on average. The maximum is still 50%. the throughput, we have about half the numbers. But definitely, if we can set it up and do some improvement for the AR64. So in summary, there are 6 glibc functions that we identified that urgently need more efficient implementations. Among them, especially the hyperbolic tangent on float, because this is actually the hottest functions, the hottest math functions that is not matrix related, due to the machine learning and AI. So what's next for us? Our goal is actually for the LibM is actually pretty simple to complete all the C99 and C23 functions and add more support on other platform and use cases. And there are already some requests to consider have a specialized implementation for fast math, and we'll see how if we have power or time to do that, and also fine-tune the performance further. So
Okay.
I'd like to give special thanks to all the LLM-libc contributors and reviewers, and especially to the COMAT project and RLM project to help us kickstart and help the project going, and all our researcher implementers in the field. Thanks. There's a link to yeah. Thank you.
Yeah, I'll make sure to post links to anything to the project on the website. And we're a little over time, so I'm just going to move straight on to the next talk. But Tway, there's a bunch of questions, like quite a lot in the Slack. So if you have a chance to get to those, I'm sure that we can continue the discussion there.
Yeah, thank you.
Okay, excellent. So our next speaker then is going to be, well, I'm not sure I'm going to say this quite right, but Nixon Ferreira. And he'll be talking about verifying an implementation of the well-clear avionics specification.
Yes. Hi, I am Nixon, master degree student at the University of Brasilia, supervised by Dr. Marcelo Ricon and Dr. Mariano Moscato, and this work also consists with the collaboration of Dr. Laura Titolo. Today, I will present to us a verified float point implementation of correct well-clear definitions. Floats are the most common computational representation for real numbers. That is, a finite representation for an infinite domain. What leads that not every real number could be exactly represented. This difference between the ideal real number and its finite representation is called round-off error. This is not the unique problem of this domain. We also have runtime exceptions, such as division by zero, not a number, etc. Writing correct float point programs could be really challenging and particularly dangerous for safety-critical systems when a misbehavior could lead the same that occurred in the Patriot missile, 1991. A round-off error made it unable to track and intercept an enemy missile, leading to 21 deaths. At least it was a long time ago, right? 2007. Automatic Dependence Surveillance Broadcast, the next generation of air traffic management, required in aircraft above 200 passengers in America and in Europe since 2020. However, this technology has a cons. It uses the old Tickers transpose that only reserves 35 bits to represent latitude and longitude. So there is the compact reporting positioning algorithm to improve the precision of this representation. However, in 2007, Australia Air Service reported that this algorithm decoded a position with a small error, just 220 nautical miles away from the actual position. Round-off errors could be really dangerous. Our safety-critical application is in the context of the integration of unmanned aircraft in the civil airspace. In the past few years, several organizations have been trying to develop solutions in that way. One of them is Daedalus, the detect and avoid alerting logic for unmanned systems developed by NASA. One of its differentials is its correctness and safety properties are formally verified using real arithmetics, and it was integrated as minimum functional operational standard in RTCA, providing three main features: conflict detection, maneuver guidance, and alerting logic. However, numerical issues could affect the computed result, so a testing basic approach was used to check the actual implementation. However, safety critical applications such as DISLs require the higher level of assurance. So our approach automatically extracts a C source code from the ideal real specification. This C code is instrumented to, whenever a divergence in the control flow may occur, emit a warning. And it's annotated with contracts claiming this behavior and bounding the round-off error of this implementation, being externally verifiable. So this approach uses several different formal methods tools, such as PVS, Interactive Theorem Prover, Precise Analyzer Code Generator for floating point programs, and Pharmacy, a collaborative framework for static analysis in C source code. These tools are integrated in a toolchain that, inputting a PVS real specification together with concrete input ranges, Precise generates the instrumented C code annotated in SSL language and PVS round-off certificates. Then, Pharmacy read this generated C code and the contracts annotated and generate verifications conditions. These verifications conditions are automatically proved by PVS using the previous generated round-off certificates and ad hoc strategies. So at the end, we have a floating point implementation that has formal guarantees of its round-off error bound and emit alert whenever a control flow may occur and automatic. That is, no expertise in floating point or theorem proof are required. So can we apply this system as it was in our case study? Not as it is. Our case study has some kind of complexity, such as high order specification, intensive use of predicates, and higher number of functions calls. So we cannot apply it. So we extend this approach, rewriting the high order declarations in Fisher order and conditionally slicing this specification, turning it manageable to the 210. So the extended toolchain now begins with a translation from high order declarations to first order, then proving the functional equivalence between then conditionally slicing this Fisher order specification and proving the equivalence between them, and for each slicing, apply the same integrated toolchain. In our case study, we divided the well-clear model based on the relative velocity in 6 slides as shown here. And to illustrate the application of the integrated toolchain, we will use this TCPA function, the time of closest point approach, a function that is in specification of DIDOMS, that receives the relative distance and velocity vectors, and if the norm squared of the velocity is greater than 0, return minus the projection of relative space vector in the relative velocity vector over the squared of the norm of the velocity. Otherwise, both Vx and Vy are 0, and then return 0. Inputting it to Precise generates two functions. The first one is purely symbolic, and the second one is with concrete values. Here we have the instrumented TCPA function, and here we have the annotations. This first line here just is the same TCPA declaration over the reals, and just a question of notation here. Everything boxed is a float point. So what Precise accurately does is replace the original guard for more restrictive ones that takes in account the round-off error. So here, instead of greater than 0, it's greater than a symbolic error variable e. Then, if it's true, return the first brand. Otherwise, instead of just returning 0, it checks again a more restrictive version of the else, then return 0. Otherwise, it may be a control flow divergence, so emits a warning. Here we have the float point counterpart of TCPA, just replacing the real operation by float point operations. here we have a practice case that states there's no control flow divergence, that is a stable path. And basically it checks if the guard is evaluated over reals and float point has the same value. Then finally, the contract, it requires as preconditions that the symbolic error variable is positive and finite. Then ensures as post conditions that if the result is not a warning, then the result of this instrumented implementation is the same of the not instrumented float point implementation, and ensures that if the result is not a warning, implies that if the symbolic error variable is a bound for round-off error of guard expression, then we are in a stable path condition. I mean, there is no control for divergences. The second function generated by Precisa is just calling the previous one, but with a concrete value for the symbolic error variable calculated by Precisa. And as contracts we have here, if the variables, input variables remain the input range, and the input variables are just rounding using rounding to nearest the ideal inputs, then the implementation round-off error is at most this value calculated by Precisa. Then once this is generated, we read it with from a C and generate verifications conditions that looks like it or it. And so at the end, we are able to analyze the whole well-colored module of Daedalus, and the conditional slicing make the process manageable to the truth gen, and also produce more simplified versions of verifications conditions. During this process, we discovered several opportunities of improvement that were reported and fixed. And in this work, we use a new axiomatic float point formalization that, besides of improving the type check time in a factor of 5, also now support special values, such as not a number in infinite. However, it impacted the previous one's strategies that were not long usable. So as future work, we aim to improve the automation degree of our approach, automatically slicing with a using hint and generating the equivalence lemmas, and also maintaining and generating more PVS strategies. So thank you very much.
Thank you, Nixon. I'll start off the question answer session since we have time. I don't feel bad monopolizing some of it. So where did you get the implementation you started with to do some of the verification work? Right? Was that directly from the did you start with just the specification, or did you start with some existing implementation that you could modify? What is the kind of path to getting the implementation that you modified?
We start with the high order specification of Daedalus that were previously developed. Then we translate it for the first order, then continue the things from here.
And is that specification being used anywhere? I know you did some of this work at NASA. Is this like proposed for some kind of standard for unmanned aerial vehicles? Do you know what the status of the specification is?
Besides of the specification, there is a C and Java implementation of this specification that were manually translated for it. So this is the current status of it. I don't know if I answered, but
okay. And there's a question from Mariano. Do you want to ask it?
Hello. Yes, I just wanted to clarify, maybe help Nixon answer. So the specification is part of a module, yeah, and in fact, they some people at NASA, they developed this specification and they manually created an implementation in C and in Java that is part now of the standard for the detect and avoid, for one particular standard for the detect and avoid. So yes, you may say that this is a all the work that they did is in fact as part of our reference implementation now.
Cool. Yeah, that makes a lot of sense. Okay, so I'm gonna move on just to keep ourselves on schedule. There's some other questions in the Slack that Nixon or Mariano you could look at. So our next speaker, and if you could unshare your screen, that would also be appreciated, Nixon. Perfect. All right, so our next speaker is Paul Zimmerman to give us an update on core math. Paul is a senior researcher at INRIA, and he's been working on core math for a little while now. So I'm excited to hear what's new.
Thank you very much, Pavel, for the introduction, and also thank you, Martin, who made a very nice introduction a few talks ago. So my goal is to talk about progress recorded in core math. So this is joint work with Alexei Sibidanov. So core math is a toy project I started last year. I guess it's a project which will be useful for the scientific community. So maybe it's my last project before I retire, hopefully. Okay, so the mission of this project is to provide on-the-shelf open source implementation of mathematical functions with correct rounding. So the idea is that this implementation can be directly integrated into current mathematical libraries. So this is not a new mathematical library. Really, the goal of core math is to die after the routines have been integrated into other mathematical libraries. And so we choose an MIT license to make integration easier. Okay, so I guess everybody knows what correct rounding is. So this is the best possible result for a given rounding mode. So this is already required by the IEEE standard for basic arithmetic, addition, subtraction, multiplication, division, square root, and the fuse, multiply, add that some people already spoke about. Unfortunately, many people don't know that correct rounding is not required for mathematical functions. So when you compute the exponential of some number, a library could give a -1. And as Martin pointed out, this is perfectly in the standard. So the goal of the project is really to push the current, the IEEE standard and also the C standard to require correct rounding for mathematical functions. And so as in the LLVM libc project, we don't only target the default rounding mode, which is round to nearest, but also the directed rounding modes, so to 0, to plus and minus infinity. And this, for example, is useful for people doing interval arithmetic. So if you look at the current mathematical libraries, so there are many of them. In fact, there are a total of 11 libraries, I know, 9 that work on CPU mainly, and 2 mainly on GPU. And they provide, all of them provide at least a single and double precision. And some of them provide also extended double, and which I call binary 80, because it's 80-bit format, and also quad precision. So among all those libraries, only LLVM targets correct rounding for now. So the goal is to push more and more of those libraries to also provide correct rounding. So if we look at the largest known errors you get when you compute with these libraries, so this is an excerpt of a table that Martin already mentioned before. So this is the largest known error for single precision. So the best library is the Intel Math library with the largest known error of a little more than half a YULP. So this is for rounding to nearest. And the worst libraries are newlib and the CUDA libraries with errors of up to 10 YULPs for CUDA for the power function in single precision, on almost 170 YULPs for the power function for newlib. For double precision, this is even worse. So the best library is also the Intel Math library with an error, a largest non-error of 1.7 ULP for the power function. And you see very large errors for the OpenLibM, the Apple library, and the Microsoft library. So the LLVM value is an artifact, and I guess this will be fixed soon. So the goal of CoreMath is that you get some 0.5 values everywhere in this table, which would be the ideal situation. And so the different libraries would compete only on the speed of their implementation and not on the accuracy. So which functions do we target in CoreMath? So we target all the functions defined in the IEEE standard, which are all those functions. So there are almost 40 different functions. Which target formats? So of course, single and double precision. Later, we will also target the extended double precision format, which is long double in the C language, at least on x86-64. And also we target quadruple precision. So that's the status for last year, at least in our ARIT presentation. So last year we did implement all single precision functions in C99, plus 3 double precision functions, the arc cosine, the cubic root, and the exponential. And at that time, out of the 26 binary 32 functions which were implemented, 9 of them were already faster than the GNU libc, the Intel Math library, and the LLVM libc. Okay, so from now I will speak about improvements from this year, from 2023. So here is an excerpt of some functions where we see for the this in a single precision, the arc cosine, the reciprocal throughput decreased from 30 cycles to 17 cycles, which is now faster than the GNU libc and the Intel Math library. For the exponential, so in double precision, this is the last row of this table, we decrease from 32 cycles to 18 cycles. So yes, these timings are produced in our test environment, which is also used by Chuli to compare to get timings for LLVM libc. And yes, I should say the Intel timings are produced using the Docker image, so which might give some artifacts. So in this year, we have implemented more functions, especially the new functions from the C2X standard. So these are the sin pi, cos pi, and tan pi, so which compute the sine of x times pi on the inverse, the corresponding inverse functions, and also some extensions of the x of x minus 1 on a log of 1 plus x to a different basis. Okay, so this is for single precision, and for double precision, we have implemented many new functions. So for example, if you want to compute a sine pi of some value, so currently the only library computing that function is CoreMath, apart from GNU MPFI, of course, but GNU MPFI is much slower for double precision. So this is a function that gave us a lot of work, the binary 64th or the double precision power function. So this is common work with Tom Ubrecht, which is a student at INS in Paris, and Claude Pierre Jeanneret with a colleague in Lyon. So we get a full code for the double precision power function with a full paper proof. So this is correctly rounded for all 4 rounding modes that I mentioned. So this is not yet integrated in Cormat, but it will be soon. And the technical paper, the technical details, sorry, will appear in the RIT paper that will soon be online. So the reciprocal throughput is about 50% slower than the GNU libc. Same for the latency, but this compares very nicely to the previous implementations in MATLib. So this is IBM Accurate library and CRLibM, which also adds some tentative implementation of the power function. And what is very exciting is that some colleagues at INRIA, Laurence Ridon, Laurent Terry, started to pop formal proof of our paper with a COC formal proof engine. Another focus on the logarithm function, so still in double precision. Some colleagues at INRIA Saclay have formally proven a part of the argument reduction that we use in Cormat. So we first reduce the argument to square root of 2 over 2 and square root of 2. And then we approximate the logarithm of t using a polynomial plus some table values. And they have formally proven that the polynomial approximation is close to z plus log of 1 plus z with some values that was given in our code. So their work will be presented also at the RIT conference. Okay, so you can contribute to the Cormat project in different ways. So you can either try to find a bug in the published functions, submit a faster implementation. Another way to contribute is to find hard-to-run cases for the different formats. You can also try to make a formal proof of some implementation. This is very welcome. Or try to work on the integration in some current mathematical library. Okay, so that's all I've wanted to present you. Thank you very much.
Thank you very much, Paul. And I also have to say that reading some of your implementations has been a good guide for some of my work. So not only are they accurate and fast, but they're also pretty readable. Let's take just a couple of questions for Paul's talk. So I'll maybe start with one of my own, which is how often are some of the new like SignPy, the C99 functions, how often are they actually being used? Because I've looked at quite a lot of C code and it seems like most people don't know about them. Do you have any sense?
I have no idea, but I guess they are not used because they are not available. So
yeah, there's like a chicken and egg problem here, right?
Yeah.
And maybe there's a question from Zach I see in the Slack. Do you want to ask that in person?
Yeah, so actually just following up on those new specialized versions of the various operators, I was wondering to what degree your previous accurate implementations guided the implementation of these new operators. Could you sort of adopt the same strategy, or did any of them require sort of rethinking things specifically for those new operators?
Basically, the argument reduction are the same as in the literature. What is specific is that thanks to the computations of hardest to run cases, as Julie explained in his talk, we know that the largest accuracy required is about, say, 200 bits. So we can really focus what is called the slow path to this accuracy. And so the idea in the first pass, you compute with, say, 70 bits of accuracy, and then you have a rounding test which tells you whether if you run this approximation, you get the correct rounding or not. On saying 1% of the cases, this rounding test fails. So you need to call a slow pass with, say, 200 bits of accuracy. And then you are sure that the output of this slow pass, if you run it, is correct.
Got it.
Do your implementations suggest any additional helper functions that would be useful to include in a later C standard? Like, I know that sign implementations almost always come with an accurate mod pi operation, right? But those typically aren't exposed to users.
So some functions which are very useful are, for example, the fast to sum, which takes two double precision numbers or two floating points in some given format with some ordering in the inputs on outputs two floating point numbers whose sum is exactly the same, but with some ordering, with some other ordering. So this is a very useful routine, and it would be nice that if it would be available in hardware.
Yeah, that's a good point. Okay, well, I want to make sure we have time for the last talk as well. There are some more talks in the Slack, but I'm going to move on to our last speaker today, who is Elmedi El Arar. He's a third-year PhD student at Paris-Saclay, and he's going to be talking to us about bounding nonlinear error operations. And Paul, I'm going to have to ask you to unshare your screen so that Mehdi can share his. Great. All right,
Okay.
Mehdi, go ahead.
Okay, I'm going to share my screen.
Okay, great. And
Okay,
we
thank
can
you.
see that.
Okay, thank you for the presentation, for the introduction. Hello, everyone. I am very excited to present you today about bounds on nonlinear errors for variance computation with the stochastic rounding. This work was done by me, Devan Soye, Pablo de Oliveira, and Eric Petit, and it is a part of Interflow project. My presentation is a summary of a publication that we have submitted. It is available in arXiv. You have the reference here. The stochastic rounding used as a replacement of the default deterministic rounding mode has shown higher accuracy in different applications such as neural networks or climate modeling. Regardless the theoretical analysis made on this rounding mode, Theo Marie and Nick Hayam have introduced a new approach based on martingales and Asimov-Ding inequality. This approach allows to compute tight probabilistic bounds of the forward error. However, me, Devan Soye, Pablo de Oliveira, and Eric Petit, we have proposed another approach based on a bound of the variance and the Benjamin-Chebyshev inequality. The applicability of these two approaches on algorithms with the linear errors, such as the inner product or Ornell algorithms, have proved the forward error and show probabilistic bounds proportional to square root nu instead of nu for the deterministic bound. To the best of our knowledge, there is no theoretical analysis or research made on algorithms with nonlinear errors with the stochastic rounding. Chan Golub and Levesque have proved the forward error of the deterministic rounding mode for different algorithms that compute the variance. And in this presentation,
Mehdi, can I just double check? Are you still on slide 2, or did the screen freeze?
Yeah, I'm in slide 2.
Oh, okay. I was just worried.
My apologies.
Yeah, I'm in slide 2 in the last, yeah. And in this presentation, we investigate 2 algorithms referred to as textbook and TruePath that compute the variance. So in my presentation, firstly, I start with some stochastic rounding properties, and I turn to algorithms that compute the variance. Firstly, I compute the bias, and I will show that these 2 algorithms are biased. But despite the existence of this bias, we have successfully extended the benefit of using stochastic rounding to these algorithms, particularly tight probabilistic bounds on the error. So throughout this presentation, let us denote f the set of floating point numbers and x hat the approximation of a real x. For 2 floating point numbers and an elementary operation, we have the standard model here, such that the relative error delta is lower than u. When using the default rounding mode, we have delta is lower than 1/2 u. For a real x, we denote the downward rounding as the biggest floating point number lower than x, and the upward rounding is the smallest floating point number upper than x. The stochastic rounding mode that I use in my presentation, I called SR nearness, and it consists in writing down with a probability 1 minus p and rounding up with a probability p. This stochastic rounding mode is unbiased. If you compute the expectation of x hat, you will obtain the exact value. A sequence of elementary operation implies a sequence of random errors, and with SR nearness, this sequence of random errors satisfies this property. The mean is 0. The relationship between the random errors, it is important, and since the independence property is not always true, Connolly, Ayam, and Marie had the excellent idea that a sequence of random errors obtained from SR nearness satisfies the mean independence property. That is a property between the independence and uncorrelated. You have the definition in the item 2, and you have the lemma proved by Connolly, Ayam, and Marie. From this property, they have construct a martingale and then use the Asimov inequality to compute a probabilistic bound on the error. So in the following, I apply this method to textbook and TruePath algorithms. Firstly, let us compute the bias. So the textbook algorithm computes the variance using the following formula. And you have the bias of this algorithm is given by this quantity. For the TruePath algorithm, it computes the variance using the following formula. And it is also biased, and the bias is given by this quantity at the first order over u. Interestingly, at the first order over u, these 2 algorithms, despite they compute mathematically the same value, but they have an opposite bias at the first order over u. Now the question is, we can extend the benefit of tight probabilistic bounds to this algorithm despite the existence of the bias. The answer is yes, of course, and we have the following table that summarizes the different bounds that we have obtained. So when n is small, for the deterministic bound, the forward error is proportional to nu, while the 3 probabilistic bounds, they are equivalent to square root nu. Here I add another method, dm, which I call dm. This method is a new approach that we have proposed in this paper, and it allows to compute a tight probabilistic bounds of algorithms with non-linear error based on a decomposition of Dubh-Meyer. On the other hand, when n is large and n square u is lower than 1, The deterministic bound, or EH or DM, are proportional to exponential NU, while the BC bound is equivalent to square root NU, which show the advantage of using this method when N is large. And also when we use, for example, low precision, because in this case the first n that we have this property gonna be small. I stress that we have extend these results to the pairwise case, and the unique that it changes is replace n by a log 2. The following numerical experiments show the forward error of the textbook algorithms in single precision and with probability 0.9. And we take some values between uniformly chosen between 0 and 1. And when n is small, the three probabilistic bounds are comparable, with a slight advantage for AH and DM bounds. However, and as we have demonstrated in the table, when n is large, EH and DM bound grow exponentially faster than BC bound, which confirmed the previous theoretical analysis. Now we compare these two, the forward error of both algorithms under SR nearness. And when, for example, when the floating point numbers are randomly chosen with the zero mean distribution, the error absorption cancel each other out, because positive and negative errors are uniformly distribution. Therefore, the two algorithms are comparable. On the other side, when we chose floating point numbers in this interval, which implies that the condition number is upper than 1, the two-pass algorithm outperforms the textbook algorithm because the mean centering in the two-pass algorithm avoids constellation and increases its accuracy, while in the textbook we have two large quantities that allow to have some absorption and implies a loss of significance. There is a great discussion in the paper about these two numerical experiments. So in this presentation, we have extend the benefits of textbook of stochastic rounding to algorithms that share nonlinear error, and we have presented a new approach to allow to compute tight probabilistic bounds for algorithms with nonlinear errors. And as a future work, we have started to explore the division case. We have some great results about the inversion case, and we hope also to have a general framework that allows to compute probabilistic bounds with SR for a lot of algorithms, or a general framework. Why not? Thank you for your attention.
All right, thank you, Elmedi. So maybe the first question, Ganesh, do you want to ask that directly?
Yeah.
Ganesh, you're muted.
Nice talk. I was wondering, what are some of the practical fast implementations of stochastic rounding? Can you mention some examples?
Okay, I was waiting for this question. Until now, units hardware implementing stochastic rounding yet to be widely available in most computer systems. However, there is some I can show you in the backup. There is Yeah, there is some processors such as graph core that support the idea of implementing with SR for binary 32 or binary 16 arithmetic, or the Intel neuromorphic shift-Louis, or some patents from, for example, IBM or AMD or NVIDIA that supports the idea of implementing hardware with SR. There is an excellent survey by Kroshi et al. that reviewed the implementation of hardware with SR, and the name of the server, the name of the survey is that.
Yeah, thanks so much. Yeah.
All right, great. Well, thank you, Almedi. I think that was the last talk of the day. So let me just do a quick outro, and that will have been FP Talks 2023. Oh, gotta share screen. Yeah, so mainly I just want to say thank you for everyone who made FP Talks happen. Primarily, of course, or like the first thank you, of course, is to our speakers. I think quite a number of the talks today were very interesting. I was super excited to hear all of the progress people have made in numerics in just the last year, a lot of updates from the previous year. But I also wanted to thank all the participants. Like I mentioned early on, FP Talks has grown bit by bit every year. And we've grown not only number of participants, but also where the participants are from, what institutions, what they're working on. And I think it's been gratifying to see, even just in the discussions on Slack that are going on right now, people are talking about ongoing work they could do or collaborations this may spark. So thank you everyone who's participated, everyone who's talked, a lot of cool topics and a lot of interesting questions asked as well. I want to give just some quick words about FP Bench and sort of how we can continue these discussions after today's talk. First of all, I want to say that there's some community building activities that I mentioned early on. First of all, there's the FP Bench Slack. I know all of you are already in it, but this is a good place to continue discussions. I have here a screenshot of one of the very first FP Talks. And so over the years, we've built up quite a number of people and quite a lot of expertise. If you have, questions you want to keep asking the speakers today or collaborations you want to potentially explore, that's a good place to do it. And I also want to call out the FP Bench community meetings. So these happen every month. They're at 9 a.m. Pacific time on the first Thursday of each month. And usually these are a good place to do kind of more work in progress stuff, right? You've seen that a lot of the talks today, those are often focused on work that's kind of done. But there's a lot of cool work in progress ideas. Does anyone have suggestions on this at the community meeting? So please do come to those. And by the way, of course, if you have some ongoing work you'd like to present, send me an email. We'll get you scheduled for one of those slots. And on the topic of community building, the other thing I do want to recall out the website fpbench.org. Let me actually give a quick view of that so you can see what's going on. If you go to fpbench.org, you'll see the monthly community meeting. You'll see past community meetings that we've held. And you can also join the Slack from here. You can join the Zoom meeting for that. You can see, of course, that all of the talks have been recorded that you've seen today. If you missed one, you can go and check that out. And then you can also see here links to some of the community resources we've put together. You can see the collection of benchmarks here. You can see some of the standards. And you can also see this directory that I mentioned early on various floating point tools that could potentially be useful for you. So that's how you can kind of continue, continue your relationship with FP Bench. I do want to call out again my advertisement that Ian Briggs will soon be looking for positions. If you're interested in an expert on math libraries or verification or synthesis, do get in touch with him. And then other than that, that's pretty much all we have for FP Bench 2023. Again, a big thank you to everyone. Very exciting talks, and been great to see everyone here.
Thanks for the great job, organizers. Yeah.
Oh, thank you, Ganesh. All right, so I'll hang out here for a couple of more minutes, but then I'll switch over to trying to get the live stream links up. Any speakers, if you can send me slides or you have links to share, maybe to a GitHub repository or a website about your project. I'll also be sending an email out, and I'll be sending a survey out to the various participants, just asking, ways that we can improve the event for next year as well. So look out for those emails. And with that, see you all.
Thank you very much.
For the help.
Yeah, absolutely. Thank you all for coming.
Bye. Thanks.
Bye. It's always great fun holding this event.
Thank you very much.
Mm-hmm.